Okay, so thank you all for coming to our tutorial. We're going to have the first talk now till the coffee break at 8:30, and after that it will be Kira's talk for the second part of the tutorial. Really exciting stuff. So let's start. So we're going to talk about the menu size of multi-item auctions. So let's first talk about this lecture and this tutorial more general. I'm aiming not to assume any prior knowledge of menu-sized concepts, so if I'm messing up on that, please shout out and stop me. Generally, please shout out and stop me if you have any question. Our goal is to really start from the basics and get you up to the level that you're acquainted with the recent results on and open questions on menu sizes. As I said, this lecture is going to be about multi-item auctions. The next lecture is going to be about FedEx and related auctions. No familiarity with these auction formats needed. And we're going to focus, at least in this talk, I'm going to focus mostly on results with only glimpses of proofs and techniques, and really only glimpses of proofs and techniques wherever I'm going to need them to make a certain point about an open question or about some research direction. The lecture or tutorial order is not chronological by papers, but rather ordered by subjects. So if you don't see any paper, it might appear later, but if it doesn't appear at all, please talk to me or email me if you think that I've missed on something that would have been worth mentioning. So our model for this talk is going to be an extremely simple model. There's a single seller who has n non-identical items that you would like to sell. And the seller has no other use for the items. So for example, if I'm a seller and I have this clicker and this pen, then I would like to sell them. I have no use for them if I don't sell them. And if I don't sell them and I want to throw them away, then I don't have any cost for that. There is one potential buyer. I'm calling potential buyer because the buyer doesn't really have to buy anything, who has a private value for each of the items. So value of 2 for this pen means that the buyer is willing to pay at most $2 for this pen. Value of 3 for this clicker means that the buyer is willing to pay at most 3 for this clicker. And the buyer's valuation is additive. So for example, for the bundle of clicker and pen together, the buyer is be willing to pay up to $5. Unlike, for example, shoes where you're willing to pay more for the pair, or maybe a red and a blue pen where you'd be willing to pay less for both of them because you only need a pen. The buyer's utility is quasi-linear in the sense that her total utility is the sum of her values for the items that she holds minus whatever she's paid so far. So if I've got both of these for $4, then my utility is 5 minus 4 equals 1. And the buyer has no budget constraints whatsoever, really a simple model. And we're assuming that the seller knows some kind of prior distribution over the buyer's values for the individual items. It may be a correlated distribution, but maybe she knows that the pen is going to be worth $2 with probability half and $1 with probability half, and the clicker is going to be worth $3 or $5 with probabilities 2/3 and 1/3, and maybe there's some correlation. That's fine. And we're going to see that when we define the mechanism later, but both the buyer and seller are risk neutral. They only care about expectations. Seller is going to care about expected revenue. The buyer is going to care about expected utility. They don't care about variance and stuff like that. So a direct revelation auction mechanism, I'm going to call this an auction later or a mechanism later. And it's going to appear on the slides as mechanism or auction, depending on how many characters I had to fit into that line, is a function that maps possibly in a randomized manner each possible buyer type. So buyer type is the valuations for all of the items. So one buyer type could be $2 for this, $3 for this. And a mechanism is a function from a buyer type into an outcome. Outcome means how many, which items do the buyer get? Maybe pen, yes, clicker, no. And how much the buyer is going to pay, I don't know, $3.50. And remember, it's a randomized function. So it could be with 50% probability, pen, yes, clicker, no. With 20% probability, clicker, yes, pen, no, and randomized payments, etc. And a mechanism is individually rational if the buyer can always opt out. What I mean by that, I mean that the expected utility over the randomness of the mechanism of any fixed buyer type is always non-negative. So opting out would give me zero utility because I would pay nothing and have no items in my hand. And if for any buyer type, whatever the mechanism gives me has non-negative utility, it means that I never want to opt out. I always want to do what the mechanism tells me to. And the mechanism is going to be incentive compatible if the buyer has no incentive to strategize. That is, if you fix a buyer type T and you think of another buyer type T prime that the buyer may want to manipulate the mechanism into thinking that the buyer is of type T prime, then the utility of buyer T from what the mechanism gives her if she says that she's of type T is greater than the utility of buyer T from what the mechanism would give her if she said that she's of type T prime. And we're, once again, only expected utilities, that's what we care about. Once again, the expectation here is over the randomness of the mechanism. So for example, individual rationality means that the mechanism can't be pay me $1 billion and get the pen, because the pen may be worth to the buyer less than $1 billion. And the mechanism could also not be tell me how much you're willing to pay for the pen and I'll charge you that. Because you'd rather manipulate and say 1 cent. Because your utility as your real type who values this by $3 is higher from telling the mechanism it's worth 1 cent than from telling the mechanism it's really worth $3. So our goal as the seller, we're going to take the side of the seller in this tutorial, is to wish to choose a truthful I mean individually rational and incentive compatible mechanism that maximizes the expected revenue of the seller. This is the part where I told you that the seller is also risk neutral. She only cares about expectations. Where the expectation is over both the prior distribution and the randomization of the mechanism. Note that everything incentive related for the buyer is only an expectation over the randomization of the mechanism because the buyer knows her type. It's not something unknown. But for the seller, it's over the randomness of the mechanism and over the prior distribution over the buyers because the seller does not know the realization of the buyer type in advance when she chooses the mechanism. So, everything clear so far? If anyone's joined, please shout out as soon as you hear something that you don't understand. I'm aiming to assume basically zero knowledge here, so if I'm skipping over anything, please tell me. You're not the only one who's not understanding anything if that's the case. So, one item. One possible mechanism, probably the simplest one, is what every store in the world does. Choose a price, offer the item for that price. Here's a clicker, $4, almost take it or leave it. You're the buyer for now. So if we're deciding to go down that route, then among all posted price mechanisms, the one obtaining the highest revenue is the one posting a price that simply maximizes this expression. So let's stare at this for a moment. So if I post a price of P is price, not probability in this talk. If I post a price of P, then my expected revenue is going to be P times the probability that the buyer accepts the offer. That is the probability that the buyer has value at least this price. So this is my expected revenue from price P. And I'm going to want to find P that maximizes this expression. Usually I would, if I have a nice way in which the distribution is given to me, I'm going to write this down, derive, find where the derivative is 0 or some on the edges or something, and find the best P. But there are also other mechanisms possible. For example, I could sell you lottery tickets. I could tell you, okay, either pay 4 to get this for sure, or pay 3 to get this with probability half. I don't know. Or maybe just pay 6 to get this with probability 1/3 or whatever. That's also an incentive compatible and individually rational mechanism. You take the offer only if you want it. That makes it truthful. And you always have the option of opting out. So one option is a posted price mechanism. There are other mechanisms, lottery tickets, etc. Here, as a standard, we've restricted ourselves to direct revelation mechanisms because it's well known that these are rich enough. But you could also think about multi-stage mechanisms where I ask you whether you like this clicker by more or less than $3. Then I ask you whether you like, whether you're rich or poor, what kind of watch do you wear, and at the end I decide on some price to offer to you. That's also a possibility, but we know that direct revelation mechanisms are without loss in the sense of the amount of revenue that they can make compared to other interactive mechanisms. And there's a theorem by Meyerson, 81, and Riley and Zeckhauser, 83. No other mechanism than a posted price mechanism can obtain better revenue. Meaning that if you want to obtain the maximal revenue from selling this clicker, the best thing for you to do is to offer the clicker for this price. Lottery tickets aren't going to help you in any way. Okay, let's talk about two items. Hopefully this is going to be more interesting, otherwise the talk is going to end really soon. So how can the seller maximize the revenue from two items? So once again, I have the pen, I have the clicker. My valuation is additive, so whatever the buyer's valuation, is additive. So they're willing to pay for both, whatever they're willing to pay, the sums of whatever they're willing to pay for each of them. And they're drawn, let's say that for a moment, for simplicity, that they're drawn independently. So the distribution that the seller knows over these two items is a product distribution. So if they're independent, so everything's additive, everything's quasi-linear, everything's independent, just optimally sell each item separately, optimally price each item separately, right? So that's also what I thought when I was first shown this, and what everyone was taught when they were first shown this. But let's look at this example. So if both item values are uniformly distributed in 1, 2, meaning that pen is worth to the buyer $1 with probability 50%, $2 with probability 50%, same for the clicker independently. So I could price each item separately and get a expected revenue of $1 for each item. Why? I could either price the pen for $1, sell it for sure, get $1, or I could price it at $2, sell it with probability 50%, get expected revenue $1. So whatever I do, if I price this I could also price this suboptimally, but there's no point in selling it for $1.50, what I could sell with the same probability if I price this for $2. So I get $1 in expectation for each of these items, however I price optimally, $1 or $2, for a total of $2. Now, here comes the nice thing. What about if I don't price these separately? I only tell the buyer, this bundle, I tie a ribbon around this. Look, special holiday sale, EC sale, pen and clicker together for $3. Take it or leave it. Take it or leave it. And the buyer is going to accept this with probability 75%, right? The only way the buyer is not going to accept this is if she values both of them at $1, which happens with probability 25%. So my expected revenue is going to be $3 times the sale probability of 75% equals $2.25, more than $2. Even more than 2 factorial dollars if you're the kind of person from the audience who likes to make these comments. So that's hugely surprising, right? I mean, this means that pricing each item separately, even though everything's additive and independent and quasi-linear and whatnot, selling separately does not always maximize revenue. So what about bundling together? So supposedly, for 2 items, it's a bit more iffy, but think about like a gazillion items. So everything's independent. So you're expecting the sum of everything to converge around something, right? Sell the bundle for a bit less than that, and you're going to sell with high probability, and everything's going to be fine. So no. Here's an example for 2 items where selling each separately is actually better than bundling. Gives you selling separately for $1 each gives you higher revenue than selling the bundle for the optimal price. And it's actually the case even for many items. What I told you about concentration doesn't work. Okay, so maybe either sell separately or bundle. Turns out this is not the case. Here's once again a very, very simple distribution. Again, an IID distribution. Each item probably 1/3 $0, probability 1/3 $1, probability 1/3 $2. And for this entire talk, whenever you see like $1 or $2, think about $1,000 or $2,000 so that there's something at stake here. Okay, we're not just trying to get a few cents more. So for this distribution, turns out that the unique optimal mechanism is to offer the buyer either one of the items for $2, the buyer chooses which one, or both for a discount of $3. That's the optimal, the unique revenue maximizing mechanism. So how about posting a price for each item and a price for the bundle, maybe a discounted price for the bundle? So once again, here's a very simple distribution. So this is not an IID distribution, but there exist IID distributions that give also this phenomenon. And offers here include lottery tickets. So the optimal mechanism here is to tell the buyer, you choose between the following three options. Either you leave, get nothing, pay nothing, or you get both of these for $4, or you get the clicker with probability 1 and the pen with probability 1/2, and you pay for this $2.50. Okay, so you can either you pay $2.50 in advance, and then you only realize whether you get only the clicker or in addition also the pen, or you could have some kind of distribution that you pay more if you get the pen or less if you don't get the pen. But the point is that the expectation would be $2.50. So you have to choose either both of these for an expectation of $4 or for an expectation of $2.50, a lottery between both of them or just one of them. So maybe choose between a few lotteries. I'm grasping at straws here. So no, it turns out this is a result by Daskalakis, Deckelbaum, and Jamos. If we take this distribution that we're going to talk about quite a lot later, it's a nice distribution supported on 0, 1 with a polynomial density function. And for this IID from this distribution, you need to actually offer the buyer infinitely, actually uncountably many lotteries in the unique revenue maximizing auction. So things are extremely complicated even for 2 items, let alone for more items, in stark contrast to what we've seen with 1 item. And this is not merely, anesthetic in the sense that we're all mathematicians and like things to be simpler and nice and a closed formula, etc. It's really, it's beyond that. It's optimal auctions are sharply hard to compute, sharply hard in the number of items. So that's very, very hard for if people don't know the jargon. They're very hard to represent to the participant. I couldn't imagine someone in the market saying, okay, you know what, you're interested in both of these. Here's a continuum of lotteries for you to choose from. And even if I could somehow represent them to the buyer, it's even harder for the buyer to find or verify the optimal strategy, right? You want to say something like, here's the mechanism, here's a continuum of menu options for you of lotteries for you to choose from. Now, you value this by 2, this by 3. Here's the lottery that maximizes your expected revenue. Now the buyer has to somehow go over all the lotteries and verify that. Or even worse, if I only tell him choose from this uncountably many lotteries, he has to actually go over all of them and figure out by himself which maximizes his expected revenue. So this is really, this isn't stuff that we can use. So a few years ago, a trend began of asking, what can we get using simpler auctions? Maybe we can get like almost optimal revenue using auctions that are much, much more simple. So to define this question, we have to say what simple auctions are, or rather what complex auctions are. So we have to find some way of limiting the complexity of auctions to say This is a complex auction, but this is a simple auction. So there are a few options to do that. One option is kind of qualitative, to disallow some features of the auction. So for example, to allow only separate selling, or to allow only packaging. So if I have like 10 items, I could say, okay, I'll price a bundle of these 2, of these 3, of these 4, and something like that. Or maybe to say I'll either sell them separately or sell all of them together as a bundle. Another option is to disallow lotteries, to say, okay, I'm going to find the best deterministic look at deterministic mechanisms and see what I get. And all of this is an all or nothing approach, in the sense that either we're using some feature or we're completely not using it. And this turns out to be too harsh, in the sense that all the features studied so far lose at least a constant fraction of the revenue. So for each of these, we're not going to be able to get 99.9% of the revenue. We could get maybe 1/2, 1/6, 1/over something, I don't know, but not 99.9% of the revenue, which is what we're going to be interested in this talk. This is, by the way, Hart, Nissan, Babayov et al., and Babayov, Nissan, and Rubinstein. All the references are on the tutorial website. Wherever you see such an abbreviation, the full paper is on the tutorial website in an unambiguated way. Another option is a quantitative one. Instead of saying we don't allow lotteries altogether, you could say we allow a few lotteries instead of many lotteries. So we choose some kind of numeric complexity measure, or rather numeric measure of an auction that we hope captures complexity in some way. And we're going to limit that and say, what can we get for auctions where where this complexity measure is not very large? So there have been a few options for this popping out over the past few years. One of them is the number of options presented to the buyer. So, for example, if I offer to you either both of these for 4 or the lottery I spoke about for 2.5 or whatnot, then each of these is an option. Another one is the length of an auction description using any language. So you choose your auction description language. You use that to describe the auction. Now let's count the length of this description. This is a very flexible auction complexity. Other things that have popped up are learning theoretic dimensionality. There's a lot of work by Jamie Morgenstern and Tim Roughgarden on pseudo dimension, and by Nina Balkan et al. On Rademacher complexity, etc., with Thomas Zandholm and Ellen Wittersek. And this is kind of a shades of gray approach, in the sense that if you allow a very, very large complexity, you're probably going to get a lot of revenue. If you limit it, then you're probably going to get some revenue. And this talk is going to be about that. This tutorial is specifically going to be about the number of options presented to the buyer. So let's define finally what a menu size means. So by the taxation principle, supposedly a buzzword in economics, though a few economists I've spoken to have kind of denied that. So at least the EC community thinks that this is a buzzword in economics at the very least. So by the taxation principle, so the taxation principle basically says something extremely simple, but extremely powerful. So every truthful mechanism, remember that we're talking about one buyer, however complex, is equivalent to specifying a menu of possible probabilistic outcomes for the buyer to choose from. So it's going to look like this. We have the menu, and each line in the menu basically says this is a possible outcome of the mechanism that you can choose. So the first line here says you're going to get item 1 with no probability. Basically, you're not going to get item 1. You're going to get item 2 with 100% probability for sure. And you're going to pay an expected of $3. You don't care how this is distributed. You only care about the expectation because you're a risk-neutral buyer. Second line is, okay, you have 20% for getting item 1. 30% for getting item 2, and you pay an expected $4. And notice that the menu doesn't tell you the correlations between these 20% and 30%, but you also don't care about the correlations because, once again, you only care about expectations. So you have a line, one menu entry for each of these, and you also have the option always of getting nothing, paying nothing. And it turns out that every mechanism, however complex, is equivalent to saying these are the outcomes you choose. And it's very easy to see that. So on one hand, obviously each such mechanism is truthful. It's incentive compatible because you always choose the line that maximizes your revenue. It's individually rational because you can always opt out. And if you're given any mechanism and you want to display it as a menu, think about all the possible ways that you can interact with the mechanism, or all the possible types that you can tell the mechanism that you have. Each such type leads to an outcome. So just make a list of all of these outcomes. By manipulating, you can get your way to any of these. The mechanism is essentially equivalent to saying, choose the outcome. So that's a very simple principle, but it's very powerful. And the menu size of the mechanism is the number of such entries in the mechanism. So not entrees, even though it's a menu, it's entries. So, and I'm crediting this here to Hart Nissan, and also that's the way it's usually credited in the literature, but it's worth pointing out that this stuff was floating around as a proof technique even before. I mean, Hart Nissan said, here's a complexity measure, let's study it for the sake of studying it. But before that, let's study this to get some other conclusions. This was floating around Brees, Chawla, Kleinberg, Weinberg, 2010, Dobzhinsky, 2011, all kind of follow-ups. We're going to talk about these papers later. So let's talk about, so this is going to be the complexity measure that we're going to talk about till lunch today. So menu size, audience, menu size. And let's just get this out of the way. Let's talk about the pros and cons before we start talking about results. So pros, very simple to explain in the sense that you could take 15 minutes and explain to someone who's not scientifically oriented at all what the menu size means. If you get a choice between 7 options, it's 7, right? It's very intuitive to define. It's tractable to analyze, as we'll see, under some hardship, but still. And something that's very nice, the base 2 logarithm of the menu size is precisely the deterministic communication complexity of computing the auction outcome. So let's say that a bit more slowly. So we have some kind of auction that's common knowledge to the buyer and to the seller. And now the seller and the buyer simply want to run this auction. So somehow the buyer has to tell the seller either his type or which menu entry he chooses, or something that has enough information for the seller to understand the result of running the mechanism. And it turns out that the log, base 2 logarithm rounded up of the menu size is precisely the number of bits that the buyer and seller have to interchange to understand, so that they both know the outcome of the auction. One side is very easy. If you have a menu of size 30, then I could send you my index out of 30 options of the option that I choose. That's log 30, rounded up. The other option, so that's always, that's one direction. The other direction, however I decide to send you my information as the buyer, eventually I'm going to have to send enough information to be able to distinguish between 30 different options. So I'm going to have to send you log of 30 bits at the minimum. So this gives a very natural interpretation to something that seems like maybe a spurious decision to focus on the number of menu items and not something else, which is nice. On the con side, it turns out that there may be auctions that are maybe intuitively be called simple, and also concise to describe, but have a very large menu size. And the usual complaint in this sense is, think about selling n items separately. This is very simple. We have 10 items, we want to sell them separately. Turns out that the menu size is exponential in the number of items. Why? Because there is a menu entry for each subset of these items. Right? Even if you sell them separately in the sense of post a price on each of them, the menu is going to say this, 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 and this for the sum of the prices, or this and this for the sum of the prices, etc. You're going to have 2 to the n minus 1 lines in the menu. And so on one side, this makes sense, because indeed there's very high communication complexity going on. You need linear communication complexity to choose in such a mechanism, because you have to tell the mechanism for each item whether you want to buy it or not. So that's linear communication complexity. So it's complex compared to poly menu sizes, which have logarithmic communication complexity. On the other hand, it seems like a simple mechanism. So saying that it's complex because the menu size is exponential in n is debatable. Amos, are you?
Yeah, I wanted to ask comment on the third point control. So even though we're talking about the deterministic mechanism, I mean the valuations come from distribution. So you could talk about the expected communication complexity, which is not the same as talking about, I mean, the deterministic is a worse question, right?
That's true.
There is something in the support that brings up this communication.
Yeah.
It could be much, I mean, the expected communication complexity could be a lot smaller.
That's true. That's true. That's a good point. Something worth looking into. I don't have anything interesting to say about that in terms of results, but it's definitely something worth looking into.
Another comment about this point. I mean, what you'd really like to say maybe is something like this. Given a certain approximation, let's look at the best menu. What that means.
Yeah.
And then you want to say, well, any mechanism, any determination mechanism achieves the same approximation as this complexity. That's not something that follows from what you say.
Again?
I have in mind, I want to get an approximation with the best menu-based option. I look at the number of entries, I pick one, two. What you're saying is that there's
running this specific mechanism is going to have this deterministic communication complexity. Right, and you're saying maybe another mechanism, simpler mechanism, could do as well and have, or could match the 1/3 that you're looking for.
Maybe so low, any deterministic mechanism.
Yeah, so we're going to look at these strong kind of results, meaning with such a communication complexity, whatever mechanism is not going to give you this. So we're going to look at these stronger kinds of results. Okay, so say that we're very disappointed with menu size measure because of this point and would like to move to a better measure. So one obvious candidate is the additive menu size, meaning that I'm going to specify a menu for you, and you're going to be able to choose any subset of the rows. So that for selling separately immediately drops down the complexity from exponential in n to linear in n, which is fine. But it turns out that additive menus are more problematic than could be imagined. There's a new result in this EC saying that however you define additive menus, so, right, I mean, there's something to be defined there once you have lotteries, right? If you pick two rows, this has 20% probability, this has 30% probability for item 1. Do you get the sum of the probabilities? Do you make two independent draws? There's stuff to be defined there, but however you define at least the natural ways that these authors have thought about, even for two IID items, the optimal revenue, for example, cannot be attained by an additive menu. We said earlier that the taxation principle tells us that any mechanism, any truthful mechanism is equivalent to a menu, meaning that the optimal revenue is always attainable using a menu. This is no longer true for an additive menu. There are distributions, even two-item IID distributions, where an additive menu would not give you the optimal achievable revenue. The fact that you're allowing the buyer to choose more than one row kills your revenue. You sometimes want to not allow them to choose more than one row in order to drive them to yet another row. So talking about additive menu complexity is a bit of a problem because it's not expressive enough to always achieve the revenue that we're looking for. So you could start saying, okay, so let's maybe have a bit in the auction description that says whether these two lines could be bought together or not together, etc. But then we're losing on simplicity. So I mean, any auction complexity measure trades off the simplicity of the definition, such as in menu side, with the flexibility, such as Kolmogorov complexity, what we talked about earlier, fix your choice of mechanism description language. So there's always a trade-off here. The menu size kind of errs on the side of simplicity, but I don't really know of another measure that's as simple and solves this problem of an exponential menu size. So to sum up, menu size is extremely simple and intuitive to define, directly implies the deterministic communication complexity. It's important to be aware of its flaws, especially as a function of the number of items n. Actually, if we're fixing the number of items, for example, and we're asking what does the menu size look like as we try and get a better and better approximation of the optimal revenue, then we don't have really this kind of argument that says, okay, here's a simple example that really shows that this complexity measure has issues, and we're actually for another parameter, not epsilon but h, that we'll define later. We're actually going to have a theorem that says no other more fancy complexity measure can fix issues with this complexity measure. We'll see that soon. So basically, it's important to be aware of this criticism as a function of number of items. It doesn't really extend, at least not simply, to as a function of other parameters that we're going to look at. I think that despite this criticism, it's important to analyze this simple measure. It's important to understand other auction complexity measures as well. We must start from somewhere, might as well start from the simplest one where you have some tractable results. And maybe someone in this audience will suggest a new and even better measure for auction complexity. It's going to be awesome. Just remember about this criticism as a function of number of items, and that also take the criticism with a grain of salt. Remember that the communication complexity is kind of high there, etc. So there is some complexity going around there. Okay, time for results. I mean, we've seen some motivating results, time for some main results. Say that we want to do precise revenue maximization. I've glanced over this earlier in the motivation section. Daskalakis, Deckelbaum and Jamos, 2013, then 2015. There exists a distribution F supported on 0, 1, such that the menu of the optimal mechanism for F times F, for two items sampled IID from F, has a continuum of menu entries. Not only an infinite, but a comparatively large infinite of menu entries. This is for the beta distribution 1, 2. Sounds kind of cryptic, but it's really simple. It's a distribution over 0, 1 with density 2 times 1 minus x. When you say it like this, it sounds simple. So it's a nice distribution with a polynomial density. And the proof is quite involved and uses something that a duality framework that they developed called the optimal transfer duality framework. Unfortunately, we don't have the scope to go into that, but it's a beautiful, beautiful framework that I urge you to take a look at. So feel free to ask me about it. I don't know if I would say that I'm an expert about it, but I'd be happy to try and answer questions. So for precise revenue maximization, we get this kind of dichotomy. For one item, menu size 1 suffices. That's the Meyerson and Riley-Zeckhauser results that we talked about. For two items, even bounded, even IID, even nice distributions, infinite menu size required. So this is a bummer. And there are basically two ways to proceed from here. One of which is to talk about approximate revenue maximization. The other one is to say, even though it looks like there's nothing between one item and two items, bounded IID, nice distributions, try to look for something in between. So we're going to take in the rest of this lecture the first approach to talk about approximate revenue maximization. Defining a model in between is actually possible. It's really exciting, and it's going to be Kira's lecture after the break. So let's talk about approximate revenue maximization, and let's start with a negative result, which once again is going to bum us out. So it's a theorem. I'm citing here the most general version due to Hart and Nissan 2013. That's true for any number of items, 2 or more. It's inspired by their proof, and the theorem is inspired by a proof of Briest, Chawla, Kleinberg, and Weinberg 3 years before that basically gives you the same thing for 3 or more items. So I'm citing the stronger version here, but it's basically due to both. So for every number of items, n, at least 2, because we know that one item is easy, and for every epsilon, and every menu size m, there exists a distribution supported on 0, 1. So this is a correlated distribution on n items, each of them in 0, 1, such that, so this is the optimal revenue attainable by an auction with menu size at most m. Go over all auctions with menu size at most m, pick the one that has highest revenue. It gives revenue less than epsilon times the optimal revenue attainable by any truthful auction, regardless of the menu size. So fix a number of items, fix epsilon, fix the menu size. You can have it huge, like 2 items, epsilon equals 1/1,000,000, and a gazillion of gazillions of menu entries, whatever, more than exponential and n more than whatever. It's not even an asymptotic result, so there's no point in talking about exponential, etc. There is some distribution for which a mechanism with such a huge menu size gives you really crappy results, less than epsilon of the optimal revenue. So basically, once again, a bummer. In particular, deterministic mechanisms cannot guarantee any fraction of the optimal revenue. Recall the deterministic mechanism is basically the most you can do is to say for each subset of the items what you're selling them for. So if you have n items, deterministic mechanisms have a menu complexity of at most 2 to the n minus 1. And this tells you that if you fix n, you fix the menu size to be 2 to the n minus 1. Whatever small fraction of the revenue you're willing to settle for, there is some distribution for which you're not going to get even that using a deterministic mechanism. And this should be compared to a result by Hart-Rennie, also Hart-Nissan 12 before that for a slightly weaker fraction, showing that for 2 items, if they're independently distributed, not correlated like here, selling separately gives at least 62% of the optimal revenue. That's a lot, right? That's selling separately is a menu size of 3. And that gives you 62% of the optimal revenue. You move to correlated, you get nothing. So once again, what do? We have 3 ways to proceed from here. One of them we can say, okay, the menu size, a specific menu size guarantees nothing. But we can ask, okay, but if we take twice as large a menu size, do we get any improvement? This improvement will still guarantee nothing as a fraction of the optimal revenue, but maybe we would know that if we take 10 times as large menu size, it would give us 10 times as much revenue. I don't know, that would be nice. Second is to relax our goal. This is about multiplicative approximation. Since we're in 0, 1, additive approximation is easier than multiplicative approximation. Since this example is in 0, 1, could relax our goal, talk about additive up to epsilon instead of losing only an epsilon fraction. Third option would be to somehow restrict the distributions. We could follow in the intuition given us to this result by Hart and Rennie and say we're going to look at independent items because things behave nicer there. Could say this is for 0, 1, but maybe let's talk about L, 1 for L greater than 0. We can bound also from below. We could do, maybe someone in the audience would have ideas for other kinds of restrictions on distributions. So it turns out that each of these will give us something nice. We'll touch on all of these in the next few slides, but really most of the talk is going to be about independent from one point on, because I'm going to try to motivate why we're going to spend a lot of time on independent. Okay, so let's start with this option of saying, okay, so a menu size, a specific menu size guarantees nothing as a fraction of the optimal revenue, but maybe if we increase the menu size, we get more compared to a smaller menu size, even though both this and this are going to be negligible compared with the optimal revenue. So here's the main theorem due to Hart and Nissan 2013. So for every number of items, at least 2, and for every f, know that this is completely unrestricted, any correlated distribution over non-negative numbers. We have the following. So revenue from one menu item is the revenue attainable by optimally pricing the bundle of all items. It's kind of intuitive, right? If you only have one option to offer the buyer, might as well throw all of the items in. It's just going to increase the sale probability. Second, this is a kind of sub-additive result. The price that the revenue that you're going to attain from a menu size of 20 is at most the sum of the revenues that you're going to get from a menu size of 5 and a menu size of 15. Okay, so you get diminishing returns in some sense. And the last point, which is a direct corollary of the second point, if you want to compare the revenue from a menu size M to your best revenue from menu size 1, then it's going to be at most an M times as much. So if selling using one menu item gives me $1,000, and now I'm going to say, okay, I'm willing to go up to a menu size of 100, then the most I'm going to get is $100,000, which is nice. It starts to show some structure. And obviously the intuitive question that you may be crossing some of your minds here is, how tight is this M? Can you relax it in some way? What can you show a guarantee of at least something, or I don't know. So it's, you have to define the question of tightness in a good way, because obviously for some distributions bundling is optimal. So for such distributions, the revenue from a menu of size M is going to be the same as the optimal revenue from a menu of size 1, because a menu of size 1 is already optimal. But what you really want to ask here is this M tight in the sense of, could I replace this M by something smaller? Is there any distribution for which I really get this factor of M? So here's a complementary theorem of Hart and Nissan saying that for, once again, fix the number of items, there exists a distribution for which you get a growth of at least M to the 1/7, M to the 7th. So you could not turn this M into less of M to the 1/7, at least in terms of asymptotics. So there exist distributions for which, if you move from from a menu size of 1 to a menu size of 1,000, your revenue is going to grow by an order of 1,000 to the 1/7. I think it's an interesting question of whether truth is M or M to the 1/7. They conjecture that 1/7 should be improvable considerably. I think it's a good question to understand. I mean, what should really be here? So this is what I have to tell you about revenue improvement with menu size. So we can move on to our next, the next of our 3 bullets, relaxing our goal to additive approximation. So here's a nice theorem due to Dolmihan and Nissan, and once again it improves upon a theorem of Hart and Nissan from a year before. So there exists some menu size that depends only on n and epsilon, so that for every n, every epsilon, and every distribution, possibly with correlations supported on 0, 1 for each item, such a menu size gives you optimal revenue up to an additive epsilon. So what's the game here? You tell me what n is, you tell me what epsilon is, what number of items is, and how much you're willing to lose. I tell you what's the menu size, that's going to guarantee it. Then only you tell me what the distribution is, and then I can find a menu with the size that I guaranteed to you before to exist that gives you optimal revenue up to an additive epsilon. This is really cool. And this is finally a useful upper bound, quotes. And let's look at the proof. So the proof technique is something extremely useful, dubbed nudge and round. There's going to be we're going to start with the optimal mechanism, then we're going to nudge it a bit, then we're going to round it a bit. Actually, we're going to nudge the buyer and round it a bit. We'll see soon. And I want to go over this proof because it's simple, because it's powerful, because basically, because basically every important upper bound that gives you up to epsilon revenue somewhere has this hidden as a stage in it, to the best of my knowledge. And because we're going to have some open questions about how to improve these bounds, and it's going to be important to understand what's going on here in order to better understand the open questions. So we'll prove, we're not going to prove this log n over epsilon to the O of n, which is due to Durkheim and Nissan. We're going to prove n over epsilon to the O of n, which is Hart and Nissan's original theorem. So here's the way to find a small menu with this size that guarantees optimal revenue up to an epsilon. So we start with the optimal menu. Maybe huge, maybe infinite, maybe I don't know, but let's start with that. Then we're going to do the nudge step. We're going to discount all prices multiplicatively. So if any menu entry cost $1,000 earlier, it's going to cost 1 minus epsilon over n times $1,000. We'll call this the nudge step because it's going to, as we'll see soon, it's going to nudge buyers toward high-priced items. As you can see, the discount is greater, like the additive discount is greater as the price is higher. Then we're going to have the round step. We're going to discretize the menu by rounding all of the probabilities to multiples of epsilon squared over n squared. We'll see soon why this resolution is good. Could have just as easily rounded the prices. I'm going to do here a version that rounds only the probabilities. The version due to Durkheim and Nissan, the improved bound, is the use of fancier log grid rather than equally spaced grid. So we're going to claim that this thing results in a. So why does this result in a menu in a small menu? Because we've rounded all of the probabilities to this grid. Okay, so there's a finite, there's actually epsilon squared over n squared to the power of n possible combinations of probabilities. Now, if any of them is priced using more than one price in the rounded menu, it's clear that only the lower price is ever going to be chosen, so you can throw all the other rows with the same probabilities away. So for each such combination of probabilities, you're going to have at most one line in the menu, one entry in the menu, so that gives the small menu size. Now I just have to explain to you why we've only lost 2 epsilon revenue in this case. The problem is that the reason that I'm doing the nudging and stuff isn't trivial is the fact that we have to be very careful when we're rounding, because even slight roundings could be like the last straw that sends a buyer who's willing to pay you a lot of money for one menu entry to a different menu entry that costs really nothing. So that's the complexity here. We could only round and get something that's like epsilon incentive compatible, but we don't want that. We would want something that's really truthful. So we're going to claim that if the original payment by some buyer type is P, then her new payment for this rounded and nudged mechanism is going to be at least P minus epsilon times 1 over epsilon over n. Why is this at most 2 epsilon less? Because P minus epsilon, okay, so you lose 1 epsilon. And then if you multiply by 1 minus epsilon over n, note that the maximum price for anything that ever gets chosen is n. Because we have n items, all of them between 0 and 1. The maximum a buyer is going to be willing to pay for all of them if he has the highest value for all of them is n. So an epsilon over n multiplicative loss is an epsilon additive loss. So we have 1 epsilon additive here at most, 1 epsilon additive here at most, total 2 epsilon. So we just have to show why if the original buyer type paid p, then she will pay at least this after the nudging and rounding. So post-discounting, pre-rounding, the utility from any menu entry originally costing less than p minus epsilon. So we have what the buyer type chose to begin with, which costs p. We have something that he's considering deviating to, which originally cost p minus epsilon or less. And the difference between the discounts is at least epsilon squared over n. Right? We've given a multiplicative discount of epsilon over n. There's an additive difference of epsilon between p and p minus epsilon. So there's an additive difference in discounts of epsilon squared over n. So earlier, if the buyer originally preferred the thing that costs p only by very slightly, or even was indifferent between this and something that cost much less, now he prefers it strictly by at least epsilon squared over n utility. Now notice that this whole rounding decreased the utility from the originally chosen entry by at most epsilon squared over n. Why? We've changed the probability of awarding each item by epsilon squared over n squared. And we have n items. So in total, we've changed the probability, the sum of all probabilities by epsilon squared over n. Anything is valued between 0 and 1. So the utility drop from the original entry was at most epsilon squared over n. So we nudge the buyer to strictly prefer his original choice over anything that costs much less by epsilon squared over n. Then we rounded, so it means that he was nudged back epsilon squared over n, but in total this could not have tilted the balance. He still prefers his original entry over anything that originally costs less than p minus epsilon. So our overall loss, instead of p, we have p minus epsilon, something that originally cost at least p minus epsilon, times the multiplicative nudge discount. That's it. That's the proof. That's nudge and round. That's the most detailed proof that you're going to see in this in my talk now, unfortunately. Okay, so that's nice. But let's recap for a moment the possibility and impossibility results that we've seen. So for every number of items, n, and for every epsilon and every menu size, so for every n and every epsilon, no fixed menu size can guarantee even an epsilon fraction of the optimal revenue. And on the other hand, for every n and every epsilon, there exists a menu size that guarantees almost everything additive. So this is multiplicative, this is additive, and there's a huge difference here. And this kind of tells, so how can they both live together in the same reality? Right? This means that you lose at most an epsilon, but you might lose like a huge factor. This means that the impossibility in the first theorem comes from cases of very, very small optimal revenues, where losing an additive epsilon means losing a huge, huge factor. And you can also see in our proof here that while we had a multiplicative loss, we also had additive loss that we, at least with this technique, we couldn't avoid. And the theorem of Hart and Nissan and Brice et al. Tells us that we couldn't avoid it, something additive anyway. So the impossibility here comes from the case of very small optimal revenues. So this gives the idea of, okay, so let's not look at distributions on 0, 1. Let's look at distributions on something, 1. That's going to rule out very, very low revenue because there is going to be some revenue to be made anyway. So here's a theorem about that. Due to Durmi-Nissan, once again, constant improve, the numeric complexity is improved over a similar theorem by Hart-Nissan. And I'm looking here at distributions over 1, h. Since we're talking about multiplicative losses, 1 comma h is the same as saying 1 over h comma 1, right? I can scale all of the prices from dollars to cents or whatever, and a multiplicative 1% is still going to be a multiplicative 1%. So I'm phrasing it here in terms of 1 comma h because that's how it appears in the literature, but you might as well think about 1 over h comma 1. It's going to be the same result. So what are they saying? There exists a menu. Okay, so tell me what n is. Tell me what's the maximum multiplicative epsilon you're going to lose. Tell me a lower bound, or tell me something about the ratio between the lower and higher bounds of all distributions. I'm going to give you a menu size that depends only on these. Then tell me a distribution that's bounded on 1h, or more generally, that has a ratio of h between the lower and upper bound. And I'll be able to give you a menu size that promises 1 over epsilon of the optimal, a menu with this size that promises at least 1 over epsilon of the optimal revenue. And as I said, you can think about L comma h, and wherever this says h, say log of L over h. That's the same because we're talking about multiplicative here. So, and the proof of this is nudge and round, and in fact, the above upper bounds that I spoke about, all of them stem from this, and this could be proven use the same nudge and round technique that I've showed you. You get n and not log n here, h and not log h, but it's once again a smarter grid would give you this. And indeed note that once you have a lower bound, what did we have earlier? We had a multiplicative loss and an additive loss. Once you know that everything is bounded between L and H, then the optimal revenue is at least L, then you could subsume an additive epsilon in a multiplicative epsilon. Or an additive epsilon in a multiplicative L over epsilon, or epsilon over L, something like that. I don't personally, apologies to the authors, I'm not particularly thrilled about let's bound everything between L and H and look at stuff as a function of h, even though it is interesting that it's log h here and not h. But I think that the reason for me to think that even though I'm not very thrilled about this, it's an interesting setting to look at, is the following main result of Durmihan and Nissan from their paper, which shows the following. For distributions supported on 1h, once again you can think about supported on LH for fixed ratio between L and H. A menu size of n, very small, can attain a 1 over log h fraction of the revenue. On the other hand, auctions with Kolmogorov complexity polynomial in n guarantee at most 1 over log h fraction. So what does this mean? I remind you that saying auctions with Kolmogorov complexity polynomial means you choose an auction description language. Menu size, pseudo, I don't know, whatever. You choose an auction description language, program the auction, describe the auction using a Python function as far as I care. Fix that language. Now look at all of the auctions that are describable in that language in a number, polynomial in n of characters. This set of auctions cannot guarantee more than order of 1 over log h of the optimal revenue. On the other hand, look at the very simple auction description language of the menu size. In there guarantees 1 over log h. So this is the result I promised you earlier when I told you there are legitimate criticisms to the menu size as a function of n, because selling separately gives exponential in n. This basically shows that if you're interested in the menu size as a function of h, a fancier menu size is not gonna make things that are possible only with an exponential menu size. A fancier complexity measure is not going to take things that are possible only with an exponential menu size and suddenly makes them possible using a polynomial complexity in the fancier measure. This kind of says that if you're looking at a function of h, this is the right measure, at least if you care about the difference between polynomial and exponential. There's no point in moving to fancier auction complexity. And to some extent, while I don't have a theorem, I do believe that it's also a good measure to study the dependence on the loss epsilon. And we'll talk about that later. So independent values is going to be what we're going to talk about for the rest of this talk. And the reason that we're going to talk about independent values is that really we care about, we care about unbounded distributions. We don't want all this bounding stuff. We want unbounded distributions. For unbounded distributions, note that only multiplicative loss makes any sense, not additive loss, right? Because if I guarantee to you that I can lose at most an additive epsilon when all distributions are unbounded, you can scale the currency so that my guarantee to you is that I can lose at most epsilon over 10 or epsilon over 1000 or whatever, which basically means that epsilon additive loss guarantee is equivalent to precise revenue maximization guarantee. So for unbounded distributions, the only kind of loss that makes sense is saying I want a so-and-so fraction of the optimal revenue. So recall that on one hand, if we look at correlated distributions and we want a multiplicative, some kind of multiplicative guarantee, we can't get anything. On the other hand, if we just bound the distributions between L and H, this is a fancier version of what you've seen in the last slide. Instead of 1 over H, we have L and H. Then we can guarantee a lot. But we'd like to restrict the distributions in some way other than bounding them. We want to look at unbounded distributions, but somehow restricted to still give us a guarantee. And this is going to be, and note that however we do this restriction, which is going to be independent distributions in a moment, nudging around will no longer suffice if we want any kind of upper bound. Why? Because you can nudge around to a equally spaced grid or to a logarithmic grid or to whatever grid you want. But once the prices are unbounded, either you're going to have to also discretize the prices, which means infinite grid. Even though it's discrete, it's going to be infinite. Or it means that once the prices are unbounded, even if you slightly discretize any probability, you have no control over the change in utilities due to this slight change, because the changes in utility is the value times the change in the allocation probability. If the values are unbounded, I meant values, not prices earlier, sorry. If the values are unbounded, you cannot discretize probability and still bound the change in utility. So we're going to talk about independent values, and here's a nice, or I shouldn't say nice because it's this G is me. Here's a theorem for every n and every epsilon. So you tell me n and epsilon, you tell me the number of items and the maximal multiplicative loss you're willing to endure. For any distributions, this isn't even independent on the bound, these are unbounded distributions. The revenue from this product, the loss from this product distribution is going to be at most 1 over epsilon. One thing nice about me giving the talk is the fact that I can save like a huge amount of slide space from not writing out my last name. you had more trouble preparing your slides in this sense. So that's, although Goldner is also a fair amount of characters. Yeah. Okay, so recall that we cannot possibly show this only using nudging around. Either we get a discrete, an infinite grid if we round the prices, or we get a discrete and finite grid for the probabilities, but every slight change in probabilities changes the value, the utilities in a way that's unbounded. So what do we do? Very, very rough high-level overview. I'm lying a bit here. First, let's scale everything so that the revenue is 1, just for convenience. Okay, everything is multiplicative. We only care about multiplicative approximations. Let's scale the currency so that the optimal revenue attainable from this product distribution is 1. Then we're going to find some h that's polynomial in n and epsilon, and that's high enough so that the probability of each good by itself being of each value by itself being above h is small. So we're going to talk about first about the double tail. So the double tail is where two or more goods are valued above h. So this is, I should have said, this is the valuation space. This is the value for the first good. This is the value for the second good. And I'm going to visualize everything for two goods here, because it's already hard for two goods. So the double tail, where there are two or more goods that are valued above h, I'm going to completely ignore buyers of these types when I'm constructing the menu. The reason is that I can do this is that it's the distributions are independent. So having one good above h, maybe with small probability, but give me huge revenue, so I'm going to have to consider that. Having two goods above h the probability is negligible compared to the revenue that I could extract from these buyers, so that I could ignore this. And this is actually the only place where this proof uses independence. The single tails, where one good is above h and all of the rest of the goods are below h, here kind of, I'm lying a bit, but kind of, the only revenue comes from the single high item. The low items that cost less than h, they don't contribute much to the revenue. I could simply not sell them. To these buyers, I could optimize the menu to sell only the high item. And since I'm selling one item here, only the high item, I could get a very small menu due to Meyerson, Riley, Zeckhauser, this kind of argument of I could simply do pricing. Actually, I have to do two menu items here, one of them corresponding to selling the item in the Meyerson, Riley, Zeckhauser case, the other one corresponding to not selling it in this case. I have to be very careful here, because whenever I modify the menu in the tail or the double tail or whatever, I have to be very wary of buyers that pay me a high price dropping down to here and paying me a very low price. So I have to be a little more careful. I have to spend one more menu entry to make sure that I keep everyone who's supposed to be paying me a lot into paying me a lot, even if they don't take the kind of equivalent of the Meyerson offer that I'm giving them. Finally, so we get from each double tail, we get like 2 menu items. For double tail, we get 0 menu items. So far, we're very, very low menu. Finally, we have the core where all values are low. And here we kind of do nudging around. I mean, it's somewhat tweaked because, once again, we have to be careful not to make anything become too attractive to people who pay us a very large price and are in the tail. But it's a not very fancily tweaked version of nudging around. So we lose an additive epsilon here. And so we have exponential menu size here, very low menu size here. Overall, we lose multiplicative epsilon and here also an additive epsilon, which is bad. But recall that we started by saying that we scale so that the optimal revenue is 1. So additive epsilon suddenly is okay. So this corresponds to doing it. The more direct way of doing this would have been, let's take a note of what the optimal revenue is and make sure that we only get an additive loss of epsilon times the optimal revenue by appropriately choosing h. But the main thing to note, even if you've completely lost me in the last 5 minutes, the thing that I want you to take away from this slide is the fact that after a lot of fancy stuff in the unbounded areas, we have the core. We do something very similar to nudging around in the core. We get exponential menu size because we do nudging around. We don't really know how to give decent upper bounds without doing nudging around, which invariably gives us exponential menu size because we have a grid for each probability or a grid for almost all probabilities and for the price or whatever. And this is the last proof you're going to see here. And all the proofs you've seen here so far basically to deliver the point of everything we know how to do is nudging around. That's invariably exponential. We're going to have to find something better. So, okay, so we have this C. We know that the menu size needed for up to multiplicative epsilon with n items is at most log n over epsilon to the O of n. Once again, the log n over epsilon is using a fancy grid in the nudge and round part. How fast must C grow as a function of n and epsilon? Does it have to be exponential in n? Does it have to be polynomial in epsilon? So here's one theorem. It's not going to immediately be clear why this is related. We're going to need another theorem to tie these two together. It's due to Babayov et al. 2014. For product distributions, there exists a constant C, slightly more than 1/6, such that if you sell separately, you guarantee at least. Okay, I'm lying here. It's the best of selling separately or selling as a bundle gives you at least 1/6 of the optimal revenue. So you take a look at the product distribution, calculate your expected revenue if you sell separately, calculate your expected revenue if you sell as a bundle. The best of these two is going to be at least 1/6 of the optimal revenue, so you can just run this auction and get to at least 1/6 of the optimal revenue. So selling as a bundle is fine, it has a menu size of 1. Selling separately, as we said, has exponential menu size. So this basically shows that exponential menu size would give you 1/6 of the optimal revenue. But we want something more than that because we already know that exponentially is going to give you 99% of the optimal revenue. So here's a theorem from also from our 2017 paper. For product distribution, the revenue from selling separately can be attained up to a multiplicative epsilon via menu size polynomial in n. So for example, for epsilon equals 1%, getting 99% of the revenue of selling separately, you could do using menu size polynomial in n. Putting these two together, you get that polynomial in n guarantees 1/6 of the optimal revenue, right? Set epsilon to be 0.1%, I don't know. So what does this mean? Polynomial in n menu size gives you 0.1% of more than 1/6 of the optimal revenue. Choose this 1/10 so that 1/10 of C is still more than 1/6. Poly n menu size guarantees 1/6 of the optimal revenue. So here's the corollary from both theorems. There exists D such that for every n and every product distribution, menu size n to the D gives you at least 1/6 of the optimal revenue. So polynomial menu size can guarantee some constant epsilon. That's nice. On the other hand, we show that sometimes you must have exponential menu size. So for the very simple distribution of n items, each of them 0 with probability 50%, 1 with probability 50%, if you limit your menu to be at most 2 to the n over 10, already exponential in n, you're gonna not get more than 1 over 10n of the optimal revenue. So if you really want 1 over 10 of the optimal revenue, or if you want 1 over n of the optimal revenue, or 1 over 10n of the optimal revenue, you're gonna need to have menu size more than exponential. Now note that maybe it would have been nice to have here something like you're not gonna oh, I'm sorry. This should be 1 minus 1 over 10n. This means that you're going to lose at least 1 over 10n of the optimal revenue. Sorry about that. So let's restate that. And this exponential menu size is going to lose at least 1 over 10n of the optimal revenue. So if you want to lose 1 over 10, so if you want to lose less than 1 over 10n of the optimal revenue, you need even larger exponential menu size. Sorry? Otherwise it would be contradictory. This should be 1 minus 1 over 10n. That's the reason that we're going to only put our slides online tomorrow. So actually, could you write down this and the BILU thing, separate versus bundle? Thanks. Okay. So we would have ideally, I don't know if ideally, we're still hopeful that we'll be able to do things with small menu size, but it would have been nice if this theorem would have said you can't get 1 minus epsilon of the, you have to lose at least, you can't get 99% of the optimal revenue using menu size less than exponential, but let's understand at least for this example why it's not the case. So we have here each good by itself uniform valuation either 0 or 1, probability 50%. Now note that when you have a lot of goods, the expected value of the buyer for all of these goods is going to be n over 2. And it's thus the sum of Bernoulli variables, right? Which means that with very high probability, the buyer is going to value the sum of all items, the bundle of all items by n over 2. That's the expectation minus square root of n, right? 1 over square root of n fraction, because that's how binomial distributions work. So if we are willing to lose 1 over square root n of the revenue, we can do this using a single menu entry. We just take the bundle of everything, we price this by n over 2 times 1 over square root of n. We sell with high probability, we get the optimal revenue up to a factor of 1 over square root n. So this kind of, the proof that we used here to show that while you can get 1 over square root n using a simple menu, you can't really get stuff of the order of 1 over n using a simple menu. This is not gonna bring us closer to showing that it's hard to get 99% of the optimal revenue rather than 99%, rather than something that grows as n shrinks. Okay, so graph time. So let's look at what we've talked about so far. We're going to have the revenue as a function of the menu size, or more precisely, the guaranteed fraction of the optimal revenue, since we're talking about the multiplicative, as a function of the menu size. So what do we know? We know that DDT show us that you can't get precise revenue maximization using a finite menu size. The Babayev et al. Result that we talked about shows that exponential in n is enough to give even 1 minus 1 over n. The lower bound that we just saw shows that polynomial n is not enough to get 1 minus 1 over n, but the approximation via separate small menu that approximates the revenue of separate selling shows that poly n gets a constant fraction. And there's a result by Li and Yao that I haven't mentioned that shows that only pricing the bundle gives you 1 over n of the revenue. And Hart and Ninsan result shows that it can't get you a constant fraction. So we kind of understand how this curve looks like. It starts here, it grows kind of in this area, ends here. And we don't know what's going on here. The last piece of the qualitative puzzle here is whether polynomial in n can get you 1 minus epsilon for constant epsilon. So for example, if you want 99% of the optimal revenue, epsilon equals 1%, can you do this with menu size polynomial in n, or must you have menu size that's exponential in n? I don't know. I think that's the most interesting open question in this field now. We'll phrase it soon. Just to see the stark difference, this graph is for independent values. What happens if we talk about correlated values? Then I remind you that it looks like this. Even remember the impossibility result due to Briest et al. And to Hart and Nissan. Finite menu size, any fixed finite menu size will not guarantee any fraction of the optimal revenue. This graph for independent does look far more interesting than this graph for correlated. Makes you kind of want to say, what's going on here? Maybe something could be done here to show something interesting that kind of looks like this and not like nothing, everything. And this is going to be Kira's lecture after the break. So very, very worth to stay here. Very worth it. So we kind of understand now for independent, up to this open question, how does epsilon behave as a function of n? But let's talk for a moment about what happens when we fix n. What happens if we fix n, say 2 items, and want to ask, okay, we want to lose at most 1% of the optimal revenue, or 0.1% or 0.001. How does the menu size grow as a function of epsilon? So we have 2 items. So recall that the results of the Skalakis et al. Show that infinite menu size is required for precise revenue maximization. So their proof actually shows that the required menu size as a function of epsilon, if you keep 2 items fixed, it's a small omega of 1, which is fancy CS way of saying as epsilon goes to 0, the menu size goes to infinity. It doesn't give, though, any lower bound on the rate of how fast the menu size must go to infinity. And for this, we have this result. So shameless promotion. If anyone's coming to Stock next week, please come to my lecture. You're very invited. I also have a poster about this tonight in the poster session. End of shameless promotion, sorry. So this result says that if you want to lose an additive epsilon, if everything's in 0, 1 and you want to lose an additive epsilon, then your menu size has to grow, cannot grow slower than 4th root of epsilon for 2 items. So for 2 items, the result of Hart Nissan, if you do the nudge and round carefully, you're going to see that 1 over epsilon to the 4th suffices to lose an additive epsilon. You need at least the order of magnitude of 4th root of epsilon. Still interesting to understand what's going on in between, but it shows that poly epsilon is necessary and sufficient. So it's the same beta distribution as in the Skalakis et al. I shamelessly ripped it off from them. Also uses delicately their optimal transport duality framework, but delicately to quantify the loss. And the question is, okay, so I just told you that I'm not very much into additive and that multiplicative is the right way to look at things, etc. So why am I showing you an additive lower bound? Because it implies a multiplicative lower bound. Recall that when you're in 0, 1, additive approximation up to epsilon is easier than multiplicative approximation up to epsilon. So if I show you that you need this menu size to show that if you don't have at least this menu size, then you lose an additive epsilon, then for sure if you don't have this menu size, you lose at least a multiplicative epsilon. And also note that this is for 2 items, but you can also take 100 items and have 2 of them distributed according to this beta distribution and have the remaining 98 of them have constant 0 value, which means that if you fix n and you just ask what's the dependent on epsilon, this gives you 1 over 4th root of epsilon for any fixed n. You may wonder at this point, okay, but what about varying n and epsilon? We'll get to that in the next slide. So for fixed n menu size, if you care about 20 items, for 20 items, if you want to obtain, to lose at most a multiplicative epsilon or an additive epsilon, you need poly 1 over epsilon menu. That's the truth. And just to take you back to the fact that we talked that menu size captures the communication complexity, I'm doing this as an example here, but it could be applied to other approximation settings that we talked about earlier. This basically gives us a tight result on the communication complexity. It says that fix n, theta of log 1 over epsilon, meaning log 1 over epsilon up to a constant, is the minimum communication complexity that satisfies the following. For every distribution f, there exists a F even with correlations, there exists a mechanism M such that the deterministic communication complexity of running M is at most this tight n log 1 over epsilon, and such that the revenue from M menu items is at least an additive epsilon loss. So if you ask this statement, what's the minimum communication complexity that you must have? That's what Amos asked about earlier. What's the minimum communication complexity that you must have in order to make sure that you don't lose more than an epsilon? It's theta of log 1 over epsilon, and even more so. And this holds even if F is guaranteed to be the product of IID distributions. So whether F is may have correlations, or whether it's guaranteed to have the product of IID distribution, independent distributions, I should say. The right answer to the communication complexity question is theta of log of 1 over epsilon. This is the kind of result that you wanted to see almost, right? Earlier, when we talked about... So you're right, we can ask about randomized communication complexity or whatever, but deterministic communication complexity, this is what we're talking about. So to sum up dependence on n and epsilon, I lost the battery is dead, so so for one item we can get precise revenue maximization using one menu entry. For arbitrarily fixed n, the menu size is going to be poly of 1 over epsilon for epsilon approximation. For taking n to infinity and fixing epsilon, for small enough epsilon is going to be poly in n for 5/6. That's the retaining 1/6 of the revenue. For arbitrarily fixed epsilon, 1%, like getting 99% of the revenue, we don't know. That's the open question we talked about, somewhere between poly n and xpan. And if we couple n and epsilon so that epsilon equals 1 over n, and epsilon goes to 0 and obviously goes to infinity, then we must have exponential menu size. And really the main open question coming from here is these question marks that were also the question mark in the graph that we saw earlier. Is it true that for every n, a menu size polynomial in n can guarantee 99% of the optimal revenue for any product distribution? Note that n here is outside the delta, so it's a product distribution. It's a distribution over r plus to the n. And I will argue to you that multiplicative losses is the right goal for fixed epsilon and for having n tend to infinity, multiplicative rather than additive, because for additive loss and values in 0, 1, the lower bound of that I talked about of Babayev et al. Implies that exponential menu size is required. Remember that we had a setting of n items, each of them 0 with probability 50%, 1 with probability 50%. And we said that to get a 1 over n fraction of the optimal revenue, you need exponential menu size. The optimal revenue there, we said, was n over 2. So to get a small enough constant fraction of the optimal revenue, you need exponential menu size. But that's kind of somewhat intuitive because the overall welfare in the market, in that market, grows linearly in n, right? We have n items, each of them 0 and 1 with probability 50%. You take n to infinity, the overall welfare to be extracted in the market goes to infinity as well. So saying that your goal is additive epsilon, where the overall welfare that you can get goes to infinity, it's going to be hard for you to lose only an epsilon because the overall welfare keeps growing as you grow n. So maybe it would have been better there to look at like additive n epsilon or equivalently additive epsilon where the values are bounded in 0, 1 over n, so the maximum welfare that's in the market is constant. This already turns out to be quite similar to multiplicative epsilon, but I really think that the right goal here, take the number of values of items n to infinity, keep epsilon fixed as a multiplicative, something that you want to lose, so there is no relation here to the amount of welfare flowing in the market. What's the menu size needed for 99% revenue extraction? And as we've talked about earlier, recall that all of the upper bounds that we know that can get 99% of the optimal revenue do nudge in around, which invariably means exponential menu size. So this boils down in its very essence to finding a better way to analyze the core, the part where everything is bounded, than nudging around. So why is there hope? Nudging around uses hardly any structural information on the mechanism, in the sense that you can take any mechanism, doesn't have to be an optimal auction, and you can round it using nudging around, right? When we looked at the nudging around argument, we said take any mechanism, nudge it a bit by a multiplicative factor, round distributions, you get a new mechanism with a small menu that only gets you epsilon less revenue than the original distribution, than the original mechanism. In nowhere did we assume that the original mechanism had some structure that corresponds to being an optimal mechanism. Hopefully, if we understand better the structure of optimal mechanisms, we could use that to do better rounding of those mechanisms than nudging around. And indeed, there were some results that were able to improve upon the exponential guarantees of nudging around due to some structural information on the mechanism that they wanted to round. So one of them is Dormihan Nissan. They achieve near optimal revenue via polynomial menu size via monotone valuations. They assume that the valuations are always such that good I is less valued than good I plus 1. You can think about ad auctions, where you always prefer to have the first ad rather than the second ad rather than the third ad, etc. So for this, they were able to derive structural information for the optimal auction for this case, and to show that they can approximate it using polynomial menu size. Another paper is Wang and Tang 14. They show sufficient conditions, or rather identify families of distributions for which the precisely optimal menu has a very small size 4, size 6. So it's very restricted. I mean, these families of distributions are kind of restricted, but maybe something like this could be done to show that larger families of distributions have small menu sizes, not for the optimal menu, but for approximating the optimal menu. There's another result in my paper that I talked about that slightly shaves the exponent. It still gives exponential menu size, but the exponent is slightly shaved under a standard hazard condition from the economics literature that gives some structure to the optimal mechanism. And as we've already seen, there's a result by Babayev et al. That achieves separate selling revenue via polynomial menu size, and that obviously uses the structure of something that maximizes separate selling revenue. In other words, the structure of the separate selling auction. So a lot of times when we have some kind of knowledge about the structure of the optimal mechanism, we can do something that's much better to nudge and round. Unfortunately, we have no idea, or almost no idea, what the structure of the optimal mechanism is, even for two items, even IID, even bounded. So that's a very large open question within multi-item revenue maximization, and having any kind of slight answer to that, or some kind of more structure in that, could maybe be something that would be useful here. So once again, the main problem, 99% of the optimal revenue via poly at menu size, even for IID items, even for bounded distributions. Additional interesting open problem, recall that nudge and round always looks like start with the optimal menu, then start to do stuff to it. Would be very interesting to get constructive upper bounds, not start with the optimal menu that we don't have any idea what it looks like and then nudge and round, but construct something with your hands. Another form of open problem is that to look only at qualitative results. So qualitatively, if we don't care about the rate of convergence or the rate of the growth of the menu, but what can be achieved or cannot be achieved, then we're in pretty good conditions. The first result is the impossibility result, saying that if you, how do you read this? For every number of items n and for every menu size m, if you take a look over all possible distributions at the worst ratio between what you can get via menu size m and what you can get via any menu size, that's 0. You get no guarantee. Second line is the result for independent distributions that says if you only take the infimum over product distributions, then you get a fraction that as the menu size goes to infinity, goes to 1 uniformly over all of these distributions. So you first take the infimum, and only then you ask whatever you can guarantee for any distribution, how does that behave as a function of m? Third one gives the same result for bounded distributions. We've talked about that, bounded from below and from above. And the fourth one here is the additive result, the additive approximation result. So when you look at this like this and you don't ask what's the rate of convergence that you have here, but only whether you have convergence to 1 or not, then things are fairly well understood. Once again, we don't have good enough understanding of the rate of conversion. That's the 99% revenue question. But it could also be interesting to ask what other kind of qualitative uniform approximation, uniform convergence results you could get via either restrictions on the revenues, such as the second and third, things here restricted to bounded or restricted to independent, maybe other restrictions. Alternatively, via other relaxations or the approximations, such as the additive one here. This could also be interesting. Another very interesting question, to me at least, is what happens with more than one buyer. Everything we've spoken about so far is for one buyer. Completely open, extend any of the results that you've seen earlier for more than one buyer. A sub-question that should be answered: how is the menu size defined for more than one buyer? The menu faced by each buyer, recall, depends on the valuations of the other buyers. Right? If Amos and Kira together participate in the auction, Amos says that his value is 12. This affects the menu that Kira sees. How do we define the menu size complexity for more than one buyer? Is it the largest menu ever showed to any buyer? Is it the sum of the menu sizes? Is it the sum of the unions of the menus? Something else? I have no idea. Or maybe don't try to generalize the menu size as a size of some menu, but try to say, okay, so with one buyer, menu size is the exponent of the communication complexity. Maybe try to analyze here an equivalent of that, the exponent of the communication complexity or the communication complexity. In this sense, it's worth to mention a related paper of Shachar Dubzhinsky from, I forget if it's Stock 16 or Fox 16, within the context of welfare maximization, so not revenue, but welfare. But what he shows is he shows this for welfare, but it's true in any context. For rich enough valuations, and additive, the communication complexity is kind of up to polynomial factors, the log of the number of possible menus ever shown to a buyer. So if you take a look at a buyer, Kira, and you ask how many menus does she ever face? So Shachar calls this Dubzhinsky calls it the taxation complexity, and the communication complexity up to polynomial factors is the log of this. He shows alternatively that the query complexity is the largest menu shown to any buyer. But both of these things crucially require the valuations to be far richer than additive valuations. These results do not hold for additive valuations. Specifically, they don't even hold to gross substitute valuations. It needs a very, very rich valuation structure for these to work. So it's related. Maybe something could be taken from here in terms of additive, which is what we've talked about. So it's interesting to ask what does capture these communication complexity, even query complexity for additive buyers, and what are the required complexity for good revenue guarantees. So summary of open questions that interest me. 99% of, that's the last time you're going to hear this in this talk, 99% of the revenue via poly and menu size in any model, even IAD, even bounded. Constructive upper bounds, don't start with the optimal menu and discretize it. Maybe even efficient construction. Significantly tighter polynomials to some of the results. For example, the m to 1 over 7 in a Hartney-Son we mentioned. So for some, m to the 1 over 6 maybe not be very interesting, but if someone could show that this is far closer to linear, it would probably be interesting. Generalizations of everything for multiple buyers, including even the definition of menu size. Other relaxations, that's the slide with the uniform convergence that we talked about. Other restrictions, such as independent valuations, bounded valuations, or other relaxations, such as additive approximation, that yield uniform convergence, uniform approximation. Other auction complexity measures, we talked about that in the beginning. And the not yet stated question underlying your EC'19 paper. Seriously, this is under the category of open questions that interest me. Do we have 5 minutes? We have 5 minutes for a quick aside. I wasn't sure if I'm going to have time for it. So I told you that Shachar-Dobzhinsky shows that there's a relation between the query complexity and the menu size, the largest menu ever faced by any buyer, for very general valuations. So let's just get a taste of what that's about. So there's a large sequence of paper, Dobzhinsky 11, Dormi-Vondrak 11, Dobzhinsky-Vondrak 12. Also a proof in a survey by Nissan 14 that's credited to Shachar-Dobzhinsky that study the query complexity of welfare approximating auctions. So not revenue, we're done with revenue, welfare approximating auctions that give a good guarantee of the welfare for combinatorial valuations. So combinatorial valuations far above additive. The buyer has a different value for each bundle of items that may be not related at all to her value for any other bundle of items. Their general proof scheme is kind of like this. 1, for any mechanism that guarantees good welfare, there exists a buyer and valuations for all the other buyers, such that when these valuations occur, this buyer faces a large menu. 2, the number of value queries to this buyer. If you don't know the valuation of this buyer and you can only do value queries, that is saying, here's the bundle, by how much do you value it? Here's another bundle, by how much do you value it, is at least the menu size that she faces. Combining these two, you get that under some realizations of the valuations, the query complexity is large. So let's just give the proof of this in 3 lines and finish our talk. So we want to show that the number of value queries, when we have completely general valuations, is at least the menu size that the buyer faces. So fix the valuations of everyone else so that this buyer faces this large menu. And let buyer I value each bundle B. We're talking about deterministic mechanisms here just for simplicity, so no lotteries, no anything. Let buyer I value bundle B by the price of bundle B according to this menu. So buyer I is completely indifferent between everything, right? Because he values each outcome by how much he has to pay for that outcome. Okay, with me? So he's completely indifferent between any 2 menu rows. But now consider what happens if we kept this same valuation, but only increased his valuation for a single bundle by a little bit, by $1. In this case, the mechanism must award him this bundle, which he values, which he gets utility 1 from, and he gets utility 0 from all other bundles. Since we can do this to arbitrarily any bundle that we wanted, because we're talking about general combinatorial valuations and not additive, if the mechanism doesn't ask the buyer about even a single bundle, it may be this bundle that the mechanism must award. So this means that the number of bundle queries that the mechanism must ask the buyer is at least the number of bundles on the menu, which they show that under certain conditions is large. So this is another aspect of something to do with menu sizes, very different than revenue maximization, very different than additive. And these papers above do much more fabulous things. They talk about restricted valuations and randomized auctions. And it's don't want to sell them short by just doing a simple proof. Last slide. So zooming into the action, a brief history of menu sizes. Someone in history started by saying one item, we can do revenue approximation, even revenue maximization, using one menu entry. Many items with combinatorial valuations, we need infinite menu size. Red is going to be infinite, green is going to be finite. Then someone said, let's zoom in between. In between, there is many items with additive valuations. Unfortunately, Reese et al. Showed that this also requires infinite menu size. Let's zoom in. What's between many items and one item? Two items with additive valuations. Hart and Nissan showed that it requires infinite menu size. Let's zoom in even more. We have here two items with independent additive valuations. A lot of our talk was about that. That's where the action happens. So it took a while, I think, to zoom in. That's why the menu size as a complexity measure only started to appear after it appeared as a proof of tools to show negative results. You can ask the same question for precise revenue maximization. I remind you that one item gives you, with one item, one menu size, one menu entry is enough. With two items, even IID, even additive, even bounded, the result of the Daskalakis et al. Shows that you need to have an infinite menu size. So we'd really want to look and say what's between one item and two IID additive bounded valuations. Seems like nothing. Turns out that a lot. This is going to be Kira's lecture after the break. Very worthwhile staying here. Really exciting stuff. Thank you very much. Questions? Okay, I guess you asked them during the talk. Thank you so much. You've been a great audience.
Complexity. Couple of quick disclaimers. One is that I just updated my version of PowerPoint, and it's been crashing a lot and making weird slides, so bear with me. I might have to flip back and forth a lot. Yeah. Second is that I talk really fast, and I'm trying not to. So seriously, feel free to tell me I'm talking too fast, and I will slow down. And if it happens multiple times, that's okay. Keep telling me. And third, please interrupt and ask questions. Like as aggressive as you like. I want you to understand what's going on. Okay. Good. I think those are my disclaimers. So let's give a quick recap of what you and I talked about before the break, so we get our minds back into it. So what I'm going to be talking about mostly is like suppose we have 3 items for sale, and our goal is to determine who gets what and who pays what, and to maximize revenue. Now, the first setting is just all the items are exactly the same, and this is what we consider single dimensional, and it's completely resolved in 1981, very elegant solutions. And what Yannai was talking about is when all the items are different. And so this is what we consider multidimensional. And he talked about the largest class being combinatorial valuations, and then he zoomed in on additive valuations, and then he zoomed in on independent valuations, and talked about what's happening in each of these classes. And what I'm going to talk about is something in between. Something that's more structured than these multidimensional settings, but is not single dimensional. Okay, so just refresher, what we're trying to do is we're trying to design incentive compatible mechanisms where you, the seller, are going to report your value, and I will decide what you get and how much you pay. And it should be in your best interest to report your true value over anything else. This is what incentive compatible means. And by the taxation principle, which we learned in the last section is not actually an econ buzzword, this is equivalent to a menu. And so So what do I mean? I mean, I'm going to give you a list of options that say you can get it with probability X and pay Y, or get it with probability Q and pay Z, and you can pick which of these menu options you want. And the way you can see this is you just take all the possible outcomes, map them to a menu, and let them pick their favorite. And if it's incentive compatible, they'll pick the one that corresponds to their goal. Okay? So this is the taxation principle. It says that all mechanisms are equivalent to menus, and what we want to know is what's the size of the menu needed to guarantee good revenue. That's what menu complexity is all about. And when we say the size of the menu, we mean the number of non-trivial options, so excluding the don't buy anything, don't pay anything option. Okay? All good? Great. Okay. So what Yannai talked about, yeah?
Is that menu to select the best option for the buyer?
So I'm saying this mechanism where you tell me your value and then I tell you what you're getting and how much you're paying is equivalent to me saying you can have option A or B or C or D, and you come and you pick. I'm not doing anything for you, I'm just offering you a menu of options. They're equivalent if the first is incentive compatible. Okay? Good question. Okay, so this was just again what Yannai said, which is that single dimensional is easy. All you need is one option. And all these multidimensional settings are infinite to do optimal, and most of them are infinite even to approximate, except for independent valuations. So we focused on that because those are finite. So the question is, what's in between? Okay, so here is in the trying to collapse the dimension of things. Here's what Yannai talked about in his two-dimensional graph and a one-dimensional graph. And we have all these different schemes of approximation, filling out a spectrum for independent valuations that are additive. And so what I'm going to talk about is, let's put one item back up on there so we can talk about what falls between. We'll talk about the static setting, where the optimal, this blue outline means I'm talking about optimal mechanisms, falls at exponential menu complexity. Budgets also falls at exponential menu complexity. An approximation settings, 1 minus epsilon approximation settings falls at polynomial, and the partially ordered setting falls at finite. And so these yellow blurbs are what I'm going to be talking about for the rest of this section. Okay. And I will, of course, define what all these things mean. You're not supposed to know. Great. Okay, so let's specifically talk about the optimal ones, the ones with the blue outlines. What this means is that before this line of work, we just had single dimensional and multi-dimensional. One and uncalculable. And so we had FedEx come along and say exponential, and then we had budgets come along and say also exponential but slightly higher. And then the partially ordered setting comes in at unbounded but finite. Okay? And also for approximation, before now, well not really before now because this is brand new, hot off the presses, but we had infinite menu needed to approximate for n-correlated homogeneous items, and for independent additive items, Yannai's new paper shows a lower bound. And so what about lower bounds for approximation? This paper shows that to approximate FedEx, that you're in between here. But it's for a very specific epsilon. It's only for epsilon equals 1 over n squared. Or on over 1 over n squared. Okay, so again, I will dive into these much more in the rest of the talk. This is just sort of like an overview of what I'm going to talk about. Okay, so what I'm going to talk about is why these settings are in between. These settings are in between because there's sort of like a bunch of single dimensional settings that are stitched together with some incentive compatibility constraints. And there are two methods that in the work so far have been really useful in talking about the menu size. And those are revenue curves and duality. And so those are the two things I'm going to cover, is the results and where revenue curves come in, and the results and where duality came in. Okay, any questions? Cool, so let's jump into revenue curves. What is a revenue curve? A revenue curve maps any price you could possibly set to the revenue you would get for setting that price. Okay? So if I have some price on the x-axis, then on the y-axis I get the revenue I would get for setting that price, which is just that price times the probability that a customer would buy that price. Okay? And you can write this in terms of the CDF. And so what is the optimal thing to do on this revenue curve? If I wanted to pick one price to maximize my revenue, what should I do? I should choose the peak. Okay, it's the highest revenue I can get from setting any price. Is clear? Okay. And so I want to map prices to revenue curves. And so what we have here is an uncertainty, with probability 1, you're going to get the item. And if you have a value below p upper, then with probability 0, you're going to get the item. So it's just 0, 1 at p upper, and the price I'm going to charge you is p upper. So this is the price of p upper. Okay? I can also have a more complex allocation rule that has multiple steps in it. So what does this allocation rule says? It says if your value is below p lower, you're not going to get the item. If it's between p lower and p upper, you're going to get the item with probability 1/3. And if it's above p upper, then you'll get it with certainty. And what I want to point out is that for this allocation rule, we can actually break it down, and instead of thinking about this randomized allocation rule, we can think about it as randomizing over prices. So for example, if we look and we notice that with probability 1/3, you're getting it if your value is between p lower and p upper. So when you're above p lower, you get it. So with probability 1/3, I'm going to set the price as p lower. And then with probability 2/3, you get it when you're above p upper. So I'll, with 2/3, set the price as p upper. So the point is, I'm randomizing over two different prices here. Price of p lower and p upper. So now my mechanism, just to be totally clear, is I'm going to flip a coin. When it's heads with probability 1/3, I'm going to offer you a price of p lower. When it's tails with probability 2/3, I'm going to offer you a price of p upper. This allocation rule is exactly the same as the first one. Because when your value is between p lower and p upper, you're still getting it with probability 1/3 over the distribution of prices and paying the same thing. And if your value is above p upper, then you're getting it whatever the price is. And what you're paying is the expected price over those randomizations. Okay? Any questions about this? Okay. And now, to relate it back to menus, you can list it out as a menu that says you definitely get it and you pay the expected price from randomizing, or you only get it when you get the lower price and you pay the lower price with the probability it comes up, or you don't participate. And again, our menu size is the number of non-trivial options, so the number of options not including 0, 0, which here is 2. And this is exactly the same as the prices that we're randomizing over in this board. Okay? So I'm going to conflate a lot: revenue curves, allocation rules, randomized prices, and menus, because there's this nice linking between all of them. Any questions about this?
I have an interruption.
Yes.
Could you try moving there's a fuzzy part of the mic. Try getting that so that it's not rubbing on your dress, if you can. Just however is most comfortable. That's my last theory for what might be going wrong. Otherwise, it's interference.
How do I make it not against the dress?
I don't know. I've never had this issue before, but it's either that or something ridiculous
How
like
about now?
interference. Yeah, no, it's totally not that. Sorry to interrupt. It's just something weird's going on with these.
Great. Cool. Any other questions? Great. Okay, so one more comment is that any monotonically increasing allocation rule can be mapped to a distribution of prices. How do we do it now that we have something continuous? Well, what's the probability that we set some specific price? It's just the derivative of the allocation rule there. And so what you're going to get back is that the probability that you're getting the item if your value is p is just the probability that a price is drawn that you're willing to pay, which with this formula is exactly the same thing. So any allocation rule becomes prices, any distribution over prices becomes an allocation rule. The number of prices we randomize over time is the menu size. Okay? Great. Okay. So how do randomized pricing map back to our revenue curve, which I just said is mapping one price to revenue. Okay? If we randomize over two different prices, what happens? We take a convex combination of them, and so we wind up with some revenue on the line just based on the combination we take of them. Okay? If we take a combination of two other prices, again, we wind up with something on the line. What if we take a combination of these three prices? Well, we're going to end up with something on the line between those two combinations. Okay? And so the point is that everything is just a complex combination of prices, and therefore the revenue for any mechanism that's randomized over prices is going to be somewhere in this complicated upper bound. Maybe it'll be, let's see if this works, maybe it'll be in here, or maybe it could be as high as possible as up here. But this revenue curve gives an upper bound of all of the possible allocation rules for randomizing over prices. Again, I'm just talking about a single dimensional setting right now. Okay? Any questions about that? Cool. Okay. So now that we have all of the possible dimensional is just one menu option because it's just the one price. So where would this complexity come in that we would wind up somewhere else on this curve? And so that's going to come up when we have multiple separate single dimensional problems that are sort of stitched together. And that's what we'll talk about next. Okay, and so the simplest setting that I'm aware of that does this is called the FedEx setting. And so this was Amos, myself, and Carlin, and Jonas Gutsubias. And what is the setting? Okay, you have a buyer, and she wants to ship a package. And she has a value of how much shipping the package is worth to her. And she has some deadline of when she needs the package by. She doesn't care if it gets there early because she's sending it away, not to herself. It doesn't matter if it gets there early. She just wants it to be there by the deadline, or else it's not worth anything to her, okay? And these pairs of value and deadline are drawn from some distribution, which may be arbitrarily correlated, and is known to FedEx. And the question is, as FedEx, how can you maximize your revenue? You can sell a discrete set of shipping options, 1-day shipping, 2-day shipping, and so on, to try and segment your market and maximize your revenue. Okay? And notice that a buyer who wants their package in 3 days is perfectly happy with 1 or 2 day shipping. That's why I've drawn this ordered graph here. Okay. So again, the setting we're in is we want to come up with the allocation rule such that when they input their value and deadline, we output the probability that they get I-day shipping and how much they have to pay. And what this is going to look like is going to be a menu that says, I'll give you 1-day shipping with certainty for $5. I'll give you 2-day shipping with probability 2/3 for $3, or with certainty for $5, and so on. And what we're going to talk about is the fact that in this setting, all of a sudden we go from 1 to exponentially many menu options. Okay? So what if we just have 2 different deadlines? What if we have buyers who want their package in 1 day and buyers who want their package in 2 days? And so what I've done here is I've separated out the marginal distributions of all the buyers who want their package within 1 day and all the buyers who want their package in 2 days. And I've drawn their separate marginal revenue curves. So what should I do if I want to set prices to maximize my revenue from the 2 different types of buyers? Well, if these were truly 2 single-dimensional problems, I could just optimize them separately. And I could say, what's the best price for my 1-day shipping? And what's the best price for my 2-day shipping? And in this case, it's actually okay. 1-day shipping is more expensive than 2-day shipping, and it turns out this is IC and optimal. And so in this case, this is optimal. However, where does the complexity come in? The complexity comes in if we wind up with a setting like this, where when we separate out our marginal revenue curves, we wind up with a curve such that when we try and optimize them separately, we wind up with a cheaper price for 1-day shipping than for 2-day shipping. So what's the problem here? The problem is that we're not actually getting this revenue. The reason is it's not incentive compatible, because anybody who wants 2-day shipping is perfectly content with 1-day shipping. They're going to go and buy 1-day shipping. It's cheaper. Okay? So this does not correctly tell us the revenue we're getting by reasoning about these revenue curves. So how can we continue to reason about revenue curves, but account for these incentive compatibility constraints that are stitching the separate problems together? And the answer is to come up with a new type of revenue curve that takes these incentive compatibility constraints into account. Okay, so what I want to reason about is a revenue curve that tells me what's the revenue I can get from 2-day shipping customers when I've already set a specific price for 1-day shipping. Are there any questions so far? Yeah.
So my guess is one of the reasons that there are different prices for 2-day and 1-day shipping is that there's actually pretty different costs to the shipper in terms of like providing those 2 things. In a setting where you don't have different costs, is there a strong reason to like separate out the marginal distributions and not just like look at the distribution over like value for 1-day shipping and only ship things on 1-day shipping? I suspect it's not. I suspect
Yeah, the reason is you can get more revenue. Okay. Yeah. The reason is, so the question is why not just treat everybody the same if you don't have any different costs? Why not just give everybody 1-day shipping? And the answer is because you can get more money out of the people who need 1-day shipping by also offering 2-day shipping. Yeah. Good question. Okay. So what if we set this price on day 1? What's the best revenue we can get? Well, originally we might have said, okay, we need to set a cheaper price than this price from day 1 for 2-day shipping, and so I picked this peak, but we know that we can actually use the iron revenue curve to get this combination of prices. And so what we really want is we want to get the revenue right here at this point. And how do we get that revenue? We get that revenue by randomizing over this price and this price. By getting exactly what this curve defines, that's the revenue from. Because this curve exists because it's the concave pole of these 2 points. So you can get the combination on the straight line. Okay, and I'm sweeping this under the rug, but it turns out this is the best you could possibly do, is to set exactly this point. And basically you're just thinking, well, I really want to set this price that's higher, so I'm going to put as much mass on this price as possible, but I'm constrained by the fact that you need to prefer 1-day shipping to 2-day shipping. Otherwise it's incompatible. And so I'll put as much mass on this point as possible, and then I'll put the rest of the mass on this next best point. And that's going to give me exactly the combination of prices that winds up here. So now I'm randomizing over this price and this price. Okay? And so it turns out that we can create a curve that exactly reasons about this. It says, well, if my price for day 1 is way higher, it doesn't actually limit me, so I can set the best price I wanted to set anyway, which is here. Which is why I have this flat line saying I'll get the revenue from setting this price. Or if the price is lower, then the best thing I can do is get the revenue right here from randomizing over these 2 prices. So the point is, this curve tells me exactly the revenue I can get from customers who want 2-day shipping, given any particular price for 1-day shipping. Okay. So how do I set my price for 1-day shipping then? Well, I also have a curve. This is the curve that tells me my revenue from 2-day customers as a function of my price for day 1. And I have a curve that tells me my revenue from 1-day customers as a function of the price for day 1. And so if I add them up, then I get my revenue from customers who want 1-day shipping and 2-day shipping as a function of the price I set for 1-day shipping. Okay? Questions about that?
You add them up. Where does the probability of having someone, mass of people who prefer 1-day shipping versus mass of 2-day shipping?
Yeah, I've multiplied the curve by that.
Okay.
It's in the fact that it's a revenue curve which accounts for the probability that a customer is willing to buy this price. It's the probability that a customer, of any customer, is willing to buy this price, which includes the probability that it's a day 2 customer. Yeah. Okay. Great. And so the point is I can do this inductively for any number of shipping options. I start with my customers who want n-day shipping, and then I write my function of the price I set on day n-1. I add on the revenue curve for day n-1, and now I have a function, a revenue curve for my customers from day n-2 for days n-2 through n. Yeah.
Do you flatline if you have like 3 days? Will you flatline in the 29?
Good question. Yes.
Okay.
Exactly. So then you're going to iron it, and you're going to post the flat line past the peak, because this is exactly what you can achieve for any price that you would set on day n-2. Good question. Okay. Any questions about the combined revenue curve? Okay, what's the point? The point is, how many menu options do we need? Well, to set our actual allocation rule, what we do is we look at the combined curve for 2 days. We say, what's the best price to set for 1-day shipping? It's that peak. And so I will set exactly that. That's my allocation rule that says that I'm setting a price that should say P1. And then I say, okay, what price should I set for 2-day shipping? Well, according to this pink curve, to get the revenue at that green point, it's to set the P on the pink curve, right? This is coming from this flat line, which is coming from this point, so I should set that price. So that's exactly the allocation rule. Okay, and so our menu options are 1 for each of the jump lines. What if my curve looks more like this? Well, I'll set this peak again at peak. So I set the price at P for 1-day shipping. And then, to get this revenue that I've reasoned about, I need to randomize over P lower and P upper. And so I randomize over the prices accordingly. And so now I have 2 menu options for 2-day shipping. Okay? So all of a sudden I've gone from 1 to 2. And so the point is, what's the worst that could happen? Is I could wind up in a case like this, where I'm saying, what price should I set on day 1? I should set the peak. And this leads us to, oh sorry, I ironed the curve, so that's what happened in the first animation. What does this price lead to on day 2? Well, it's ironed there, which means that I need to be randomizing over the peaks. So I wind up with 2 prices for 2-day shipping. And what do those lead to? Well, this one I've also ironed, so the peaks that give me that price, and so on, and all of a sudden we're up to exponentially many prices. Because they keep splitting when I've ironed. Why have I ironed? Because the distribution is wonky, and so to get the maximum amount of revenue, I have to randomize over prices. Questions about that? Yeah.
So the expected price of day 2 is the same as day 1?
The expected price of day 2 is the same as day 1.
But if you look at day 3,
Yeah.
why wouldn't you randomize over the 2 middle ones? Why do you do randomization like it's still in the middle?
Yeah, so now to make IC work with day 2, I need to have the same expected prices at both points. If I only randomize over the middle 2, so it's sort of weird in this case because it's a straight line, but if it weren't a straight line, if I had drawn my curve slightly better, yeah. Okay. Good. Okay, so what's the point? The point is that we have an upper bound of the many complexity. The worst case is that at any point we're going to split into 2 more points. We know that the upper bound is this concave upper bound, which is achieved by just picking pairs of points and drawing lines between them. So to get the revenue from any of the upper bound, we just have to randomize between 2 points at a time. So we'll only ever double as we go, which is why we end up with exponential. The lower bound. Okay, great. The lower bound comes from this paper by Gonczarowski, Ariel Schwartzman, and Matt Weinberg. And basically what they say is that these revenue curves can exist. In fact, pretty much for any revenue curves, they can exist, but we'll get into that more later. And so the point is that this many sizes type is exactly exponential. Okay? So all of a sudden we have a new point on our spectrum between 1 and uncountable infinity, and it's exponential. Any questions? Okay. What about approximate many complexity for the setting? So this is what's also addressed in the paper by Gonczarowski, Ariel, and Matt. And the point is, how can we achieve good revenue if we have to limit the number of prices that we randomize? And the answer is, well, since we only randomize over these unironed peaks, what if we just limit the number of unironed peaks? Okay? And so, for example, we could take this curve, we could scale down the curve and say, we're looking for a revenue curve that's going to lie in between so that it'll give us a good approximation between 1 and 1 minus epsilon times this curve. And now I'm going to set up a bunch of points because I'm limiting, and now I'm only using 6 different points to randomize over, so I know that my menu complexity is limited. I can't randomize over more than the 6 points. And I'll just connect them. Yeah. Okay? And so the point is, if I use curves like this, and I know that my revenue is in between optimal and 1 minus epsilon optimal, and I know that I've limited the number of prices I can randomize over, I'm in good shape. Okay? So the point is that, again, the menu size is limited by the number of points that support the curve. And so if I were to have a price imposed from an earlier deadline, what would I do? It's going to hit this curve here, and I'll just randomize over the 2 points. Whatever happens, I can only randomize over the points on this curve. Questions about that? Okay, so I'm not really going to go into any greater detail about this paper, but feel free to bug Ariel after the talk. And so the point is that they wind up with an upper bound that is order n squared over epsilon to get a 1 minus epsilon approximation. And they wind up with a lower bound that is order n squared when epsilon is order 1 over n squared. Okay? And this is one of the first lower bounds that we have for a fixed epsilon until Yannai's taught the rest of this paper. But it's only for epsilon equals order 1 over n squared. Okay? And so let's recap what we've talked about so far. First, we said that the splitting into multiple prices is happening because of the incentive compatibility constraints between the deadlines. Then we said that these revenue curves, the fact that we're using this concave upper bound and these lines between them, limits how much prices can split because they'll only ever split into 2 at a time. Then we said, essentially any combination peaks and valleys of a revenue curve can exist. And this is due to Ariel's paper again, which I want to point out, I'm hiding a lot of details, and basically you can't necessarily have like the extent of peaks and valleys that you want, but you can have the peaks and valleys that you want, which is really what's important when it comes to how many menu options you need, but not necessarily the degree of approximation or how much revenue you're losing. And finally, that when it comes to approximate revenue, by limiting your menu complexity, this reduces to polygon approximation by just approximating the revenue curve. So the bounds on the previous slide came from, the upper bound comes from polygon approximation. The literature on polygon approximation improves slightly in this paper. Okay, questions about revenue curves? This is part 1, and I'm going to launch into part 2 on duality. So you should take away that revenue curves are a very useful method for reasoning about how many prices we need to randomize over and the menu complexity. Okay, great. So next we're going to get into a duality approach, and specifically using complementary slackness to reason about when the allocation probabilities must be distinct, leading to more menu options. Okay, so for example, let's go through the FedEx example again using duality to make sure we understand the duality, and then we'll move on to other settings. So what's the problem we're trying to solve? We want to maximize our revenue, subject to incentive compatibility, which says that we should get more utility for reporting our true value and deadline than any other value and deadline pair, and it should be a feasible allocation. Okay, for reasons I'm sweeping under the rug, in this setting, it simplifies to a much, much nicer optimization problem. We can simplify a lot of these constraints and translate them because of the fact that, as I've said a few times, it's kind of like single-dimensional problems that are stitched together. And so we get some perks of it being single-dimensional like, such as the payment identity and incentive compatibility constraints for using. Okay, so we wind up with this nice optimization problem. High-level duality. Usually, the type of duality you're probably familiar with is that you have some primal that's a maximization problem and some dual that's a minimization problem. And these are duals of each other. And what you find out is that the solution to the primal and to the dual, this pair is optimal together when complementary slackness is satisfied and feasibility. And so what is complementary slackness? It means either your constraints in the primal are tight, or the matching dual variables must be 0. And likewise, if your constraints in the dual are tight, or the matching primal variables must be 0. So you have this correspondence between constraints in one and variables in the other. Okay? And so what we'll be using is Lagrangian duality, or partial Lagrangian duality, which basically says I'm going to take my constraint that g of x is greater than or equal to 0 and pull it into the objective function by multiplying it by a dual variable. And so what the dual means in this sense is just that you switch the order of max min to min max. And what complementary slackness means in this setting is it only goes one way. Either your constraints in the primal must be tight, or your dual variables are 0. Okay? So this is just like crash course. You don't need to really know how to work with this, but to motivate what comes next. Questions? Okay. So again, I swept under it, but this is the primal we're actually working with. And what you should notice is that because we're in this nice, highly structured setting, we only have this one form of primal variables, which is the allocation rule. We use AI, which is just the probability that I'm going to give I-day shipping to a bidder who reports that their value is V and their deadline is I. So I just reduced it down into much fewer variables. So now I'm saying maximize my revenue subject to I should report my true deadline, my true value, and my feasible. Okay? And so I guess one comment I'll make is that this I should report my true deadline turns into this area under the allocation rule constraint, which we'll see more later. But I'm not expecting you to know where this came from. I'm just asking you to take this at face value. Okay? And so I will have dual variables that correspond to my constraints, and then I'm going to move them into the objective and take the dual and regroup some terms. And so now I'm just going to show you the dual that comes out of it. So this is the great. I swear they're perfect on here. This is the dual that comes out of it. And the point is just that we have this min-max problem for this nice term of multipliers. And so this is just a function of our other dual variables, and you don't really need to worry about what this exact function is, but the point is that the dual variables that correspond to the constraints I just talked about are just going to change this objective that we're trying to deal with. Okay? And so what we wind up with is that if we have an optimal primal and dual pair here, we should be able to change the variables to further minimize. And we should have complementary slackness, which means that either our constraints in the primal should be tight or our dual variable should be 0. Okay? Now we're going to zoom in on each of these things and play with them a little to make sure we understand what that means. Okay. So what I've drawn here is an illustration of this function phi, which is a function of the dual variables. It's increasing. It's going from if I report my value as 0 to if I report my value as high as possible. And I mentioned in the first part that he doesn't like when things are bounded at h, and I want to note that everything should work out smoothly for infinity, but we're going to simplify it and talk about h.
I qualified this.
Yes, he did qualify. Okay, good. So the point is, if I point at any point on here, I'm going to talk about this f times phi at that point, where that point is day I shipping and value v on the vertical axis. Okay? Okay, and so these signs just mean that here f times phi is positive, here f times phi is 0, and here f times phi is negative. And so my question is, if I'm trying to find an optimal solution to this problem, what should my allocation rule be in the region where f times phi is positive? What do I want to set a to maximize this quantity, given that this quantity is positive? 1. We want to set it as high as possible with 1. So again, a has to go right. This has to be between 0 and 1. Okay, and now in this region where it's negative, if this quantity is negative and this has to be between 0 and 1, what should we set it to maximize? Picking a to maximize.
0.
0. Good. And what about when this term equals 0? What should we set a to maximize? It doesn't matter. It doesn't matter. Exactly. So the point is that a needs to maximize this term. Okay? And so when it's positive or negative, we have no control over it. It better be 1 or 0. And if it's in between, then we're going to deal with what it should be exactly. Okay? So the interesting stuff is going to happen in this in-between region where this f times phi, the virtual value, is 0. Okay? Questions about that? Okay. Okay. Let's talk about our dual variable alpha, which is going to correspond to the fact that I want to report my true deadline over any other deadline, or rather specifically one deadline earlier, since the structure of the setting says that's enough to imply over any other deadline. Okay? So I have my constraint and I have my dual variable, and this is again area under the allocation curve that we're talking about. That's either going to be positive, the difference is going to be positive or 0. Okay, so here I have 1-day shipping and 2-day shipping, and again I've drawn my virtual values, with my value going vertically. And my question is, what happens if I know that alpha, which I'm going to visualize as going from day 2 to day 1 at value v, is positive? Complementary slackness says, if alpha is positive, this constraint better be tight. Okay, so if this constraint is tight, this means that the area under the curve is the same, and I'm finding why, but the area under the curve is just equal to utility here because it's single dimensional, like, so we have the same thing. If that didn't mean anything to you, that's fine. That's just for those who understand. Okay? And so the point is that the utility between day 2 shipping and day 1 shipping should be equal. The area under the curve should be equal. This constraint should be tight where alpha is positive. That's just what complementary slackness means in this case. And so, for example, they don't have to be the same curve. They just need to have the same area under them at that point. So at x, I better have the same area under the blue curve as under the red curve, which I do have here. Okay? These are the same size boxes. They're just stretched in different dimensions. Good. Question? Okay. My other type of dual variable is lambda, which corresponds to the fact that my allocation rule should be monotonically increasing. Okay? And this lambda is going to to correspond to ironing, as we were talking about before in the revenue curves. Okay, and so what I've drawn here is, again, I have my virtual values and my deadline I and my value. And what this oval means is it means an iron region. Okay, it's an iron interval. And what it means is that in this full oval, I want to have lambda being positive, not 0. And then at the endpoints, I want to have lambda equal 0. So that's what an iron interval is. It's a whole region where lambda is positive, but at the endpoints, it's equal to 0. So you should think of this as the flat line between two peaks on the revenue curve. Okay, and so what complementary slackness says here is that if lambda is positive, the derivative of the allocation rule must be 0. What does it mean that the derivative is 0? It means that the allocation rule must be constant. Okay? And so what this means is that you're going to basically have equal utility within deadline I for different values. But really what I want you to remember is that the allocation in this full interval must be constant. I cannot increase it in this interval because lambda is positive and complementary slackness says to be optimal, you cannot increase it. Okay? So let's recap what we just said. Because the allocation rule maximizes this quantity in the dual, if the virtual values are positive, it better be 1. If the virtual values are 0, it better be 0. Or negative, it better be 0. Okay? The second thing we said is with lambda, if we're in an iron interval, because lambda is positive, then the allocation rule better be constant in that interval, which means the allocation within that interval is equal to the allocation at the bottom of that interval. And what about complementary slackness with alpha? If alpha is positive, going between the two deadlines, it means that utility is equal across the deadlines, or the area under the allocation rule needs to be equal. Okay? So I'm going to abbreviate this by just key, and I'm going to ask you to say these things back to me. Not on this slide, in a slide or two, but I will have this key on the slide, but you should know what this means. Again, virtual values are positive, allocation is 1. Virtual values are negative, allocation is 0. Lambda is positive, allocation is constant, alpha is positive, area under the allocation between the two deadlines is constant. Okay, and so now we're going to use this duality technology to rederive exactly what we did in the first half of the revenue curves. Why? Because then we're going to go through more complex situations where this technology is useful. Okay. Yeah?
Can you always study? Isn't there other constraints of the that you get with?
Why you might not be able to set it to 0 or 1?
Yeah.
In these settings, no. In more complicated settings, perhaps, but I believe that the virtual values will always be 0 everywhere that things are constrained. Okay. Here's an example of what my dual looks like. And I've got my key in the corner to help us out. What do we know about on day 1 shipping? Notice that we have positive and then negative. There are no zeros. So what does that tell us? Did you say what?
A single price.
A single price, exactly. Yes, a single price. We know that where it's positive, the allocation has to be 1. Where it's negative, the allocation has to be 0. That's just a price. Exactly. Good. Okay, what else do we know? Well, we've got these alphas. This is depicting that alpha is positive going across. What does it mean when alpha is positive going across? What does their box say when alpha is positive?
Utility equal.
Yes, utility equal at B. Exactly, good job. So what does that mean? That means that the area under the allocation rule needs to be the same. So for the area under the allocation rule at B to be the same, the area under the red curve is 0. So the area under the other curve needs to be 0. Good. And for the utility to be the same at X, the same area under the curve, what do we do? Well, we have one more constraint, and that's the fact that here we have an iron interval. When we have an iron interval, we have lambda as positive, which means that the allocation needs to be constant, right? It can't be increasing. So here we have the only possible solution. We needed to have 0 area here. We needed to have the same area at X, and we needed to not be increasing from Z to X. Okay? So this is the only possible solution that satisfies all of our complementary slackness constraints. And what do we wind up with? We wind up with too many options. We're randomizing between between prices in C and X. Okay, so this is exactly what we had before when we split the prices, but now we're using that through complementary functions. Questions? Okay. So, again, what's the worst case for FedEx is when we have a dual that keeps exploding, and we wind up with exponentially many, many options, right? We just have the exact same complementary slackness constraints coming from these alphas being positive and our lambdas being positive. Okay, so again, as we said, you get exponentially many prices for deadline I, which means exponentially total, and this is perfectly tight. Okay, so let's go to more complex settings from here now that we have this duality technology. The next generalization is the budget setting. So here, we still have the package to ship, how much the item's worth to you, but we also have a budget of how much the seller can afford. They cannot go over their budget. They just cannot pay more than it. And the question is, how do you set up options for different budget amounts to maximize your revenue? So this is a study by Goldner and Matt Weinberg in EC'17 last year. And the result is very similar technology using duality, and it says that you wind up with at most exponentially many prices, but more than FedEx. Okay? So this is all I'm going to say about this paper, but the point is that it does something similar in terms of optimal mechanisms and gives a different many complexity for a different setting. Okay. And the setting I really want to dig into is the partially ordered setting. So this is a paper by Goldner, myself, Ariel Schwartzman, and Matt Weinberg. So what's the setting we're dealing with here? Our customer has a certain service or set of good or interest that they want. So this previously maps to the deadline they wanted, and they have a value of how much that set is worth to them. So for example, I could be selling Wi-Fi, or Wi-Fi and phone together, or Wi-Fi and TV together. Those are the three options that I'm selling, and my customers might be interested in any of those three bundles. Now, the distribution over what that interest is, so G here is one of these three bundles. It's either Wi-Fi, Wi-Fi plus phone, or Wi-Fi plus TV. Okay? And these are done from a joint correlated distribution that is known to the seller. And there's also some structure over this, because if I just want Wi-Fi, if you give me Wi-Fi plus phone, I'm happy. That's fine. I can dispose of the phone. I just need Wi-Fi. However, if I want Wi-Fi plus phone, I'm not happy with any of these other options because none of the other options give me a phone. Okay? Does this sound clear? So this is actually equivalent to single-minded valuations, where you're selling a bunch of different items and a bidder has some set of items that they want and they're only happy if they get at least that set. It's slightly different because our partial order might not be the full set of options, but you can just think of that as we know the prior distribution, so we know where there's measure 0 of there being customers of that type. Okay? Questions about setting? Okay, so let's go back to our duality setup. Now instead of dealing with just our deadlines going 3, 2, 1, we're dealing with our partial order going from C, which you can think of as Wi-Fi, to A or B, which you can think of as Wi-Fi plus phone or Wi-Fi plus TV. Okay? And so what changes? The difference is just now, instead of having prefer one deadline to the other, we're having prefer the one option up, whatever one option up is. So maybe one option up is Wi-Fi plus phone, maybe it's Wi-Fi plus TV. You can have multiple one option ups. Okay? So one option up in the partial ordering over the items, or the option. Okay? Otherwise, it's exactly the same setting. We have our prefer your utility for your current option to one option up, corresponding to alpha. The allocation rules should be monotonically increasing, corresponding to lambda. Otherwise, exactly the same. Okay? So how do we visualize this setting? So now we have, again, going from C to both A and B instead of just 2 to 1. And so this means there's an alpha from C to A and an alpha from C to B. Now, you should always prefer C to A or B. That's incentive compatibility, at least as much. And if alpha is positive from C to A, complementary slackness says that your utility must be tight, right? And so what does that mean? I'm C, I always But now I prefer C as tightly as A. I have equal preference for A and C, which means what between A and B? It means that A is preferable to B. At least is preferable. So this is really key, and this is where the rest of the complexity is going to come from, is the fact that because you have this option C who's interested in both A and B, if there is this dual variable being positive between C and A, because of incentive compatibility, now A is being directly compared with B. Before I couldn't compare A and B. Phone and TV, nobody wanted both. But because C would be interested in both of them, now it can directly compare A and B. Okay? Okay. So let's go back to our setting. I'm going to not show you C or the Wi-Fi option because it's always, like, if there's an alpha, it's always coming from C. So I'm just going to show you where alpha is positive, but it's always coming from C and either going to A or B. And I'm going to alter my box and just say now we have this extra thing that says if alpha is positive, it means that A better be preferable to B at that point. Okay? Or have at least as much area under the curve. Okay, I may have gone too fast there. Questions? Great. Okay, so let's talk about the lower bound for this partially ordered setting now. So we're going to use really similar ideas to that of FedEx, but because we're dealing with this A versus B, it's going to be more complex. So here I have our key. What do we know about option B, given that it goes from positive to negative in those zeros? The allocation rule must be a price. Okay? It's got to be 1 when it's positive, 0 when it's negative. That gives us a price. So we know that the allocation is 1 up in the positive region. Okay? What do we know at x1? At x1, what this arrow indicates is that alpha coming from C into A is positive. Alpha is positive, and alpha being positive into A means that A is preferable to B there. Which means that the area under A's allocation rule needs to be at least as much as the area under B's allocation rule. Okay? And so how can we make that happen, given that the allocation is 1 on the right? The only way to possibly make it such that A is preferable is for the allocation not to be 0. I better be giving something of A at that value. Okay? So the allocation needs to not be 0. It needs to be positive. But now we're in an iron interval. And what does being in an iron interval means? It means that lambda is positive, so our allocation rule is constant. Which means that since the allocation is positive up here, what must it be at the bottom of the interval? It must be positive. It's got to be the same. Exactly. Great. So now, all I've come to understand so far is that it better be 1 over here, and it better be not 0 over here. Let's expand this into a slightly bigger example. We have the exact same reasoning that we just did, but now we've got more going on the right. What we have is that at x2, we also know that B must be at least as preferable to A. We know that at x2, you're getting something from A, which means that if B is at least as preferable, at x2, you better be getting something. Right? So what that means is that the allocation rule is positive. And so what does that mean? We're in an iron interval again, which means that the allocation rule is constant, equal to the same thing at the bottom, which means that the allocation rule at the bottom better be positive. So far, all I've done is I've said, it better not be 0 at all these points. Next, what I'm going to do is tell you, it better be different at all of these points. I'm going to work my way back up the chain and tell you why it better be different at all these points. So we know it can't just be 0. And then I'm going to say, if it's not 0, it better be different. And so what's the point is that we're going to wind up with all these different probabilities, which means different menu options. Okay. And we're done. Okay. Good. So the point here is whatever my allocation rule is for B at this point, our lower B, say this is my allocation rule, it's the red curve. In order for at x2, for A and B to be equally preferable, because notice that alpha is actually positive to both, so I better like them the same. I need to have the same area under the curve, under the blue curve for A at x2 as I do for B. Okay? And so suppose whatever the allocation rule to our lower B is, suppose I use the exact same probability or smaller at RA, Then because it's constant again, up to x2, I can't change the allocations up to x2. What it means is that my utility is going to be smaller. So in order to have the same area under the blue and the red curve, I'm not saying something very complex. All I'm saying is because they can't increase from that point to x2, to have the same area under the curves, it better be that the blue curve is at a higher point on the y-axis than the red curve. I'm not even telling you what that point is. I'm just saying it better be higher because it starts later. Does that make sense? Okay. So all I'm saying is that the allocation rule here better be just at least strictly larger than it is here. Okay. So the point is, all the way down we said it better be positive, and then now I'm saying that because it's positive, because it's at some point on the y-axis that is not 0, the blue curve needs to be strictly higher. And so the point is I can now extend this chain, these overlapping iron intervals, as long as I want, and do the same reasoning. I can say all the way down, okay, well it needs to be 1 on the right at B, and because it needs to be 1 on the right at B, then to have equal preferability at x1, I better have the allocation rule for A be positive. And then because the allocation for A is positive, and I'm in an iron interval, it's positive lower, to have equal preferability at x2 with B, now this also has to be positive. And so all the way down I've got these iron intervals pushing the allocation being the same lower, until I reason all the way down to say they all need to be positive. Then from the bottom, I do the reasoning upward saying, okay, I set whatever I set here, what do I have to set over here to at xm have them be equally preferable? It's got to be strictly larger. And I reason all the way back up saying that it's got to be strictly increasing at each of these points that I hit. Okay? So the point is that if they're all positive and they're strictly increasing, then I wind up with m different points. I haven't said how do I satisfy this. I'm just saying that it's a lower bound. I at least have to satisfy this. So I'm winding up with at least m different probabilities that I'm offering to the buyer. Okay? So the point is that through complementary slackness, if I have this kind of chain structure, I'm saying that I have to have at least for any m, I can design this chain structure with n intervals such that I'm offering at least m options. Okay, but I just sort of drew this chain structure and I didn't tell you why it could exist. And this is similar to the fact that before I was drawing revenue curves and I didn't tell you why they could exist. And so there's also a theorem that basically says, for any rule, whatever it is, as long as it's only really dictated by where the virtual value is positive and negative, what are the iron intervals, and where is there positive alpha. I'm not telling you to what degree they are, just that they're either positive or 0, then this exists. And so what that means is that the bad rule exists. Okay, so we talked about this structure that could be really bad, and now I'm telling you that it also exists, which means that the many complexity is going to be unbounded. For any m, I can require you to need at least m options. Okay? So we know that we need at least m options, but in the beginning, I told you that this is lower than the infinite many complexity. So now let me talk about why it's always finite, even though it's unbounded. Okay. The point was, let me tell you what I'm snooping under the rug. What I'm snooping under the rug is how we go from this bad structure to actually satisfying all these constraints and showing that there is an optimal mechanism. Turns out there is, that's a large part, but we're going to skip that and just assume that there is some optimal mechanism that corresponds to it, and it corresponds to exactly the points I told you about. We're saying it's increasing at these points and you can satisfy all of those equations. Okay, the point is that we've got this chain of overlapping iron intervals, and with specific points where alpha is positive. And if there are m of these overlapping intervals, then the menu size is actually, at most 2m, so it's finite. I'm sort of sweeping this out of the way, but as long as there's only m, I only showed you where m things came up. Okay? The problem is, why couldn't it be infinite? Why can't I have a sequence of infinitely many intervals, this chain going on forever? I could. I absolutely could. But it turns out that by some cool fact, it's still finite. And the reason for this is I have infinitely many iron intervals, but they're bounded at the bottom by 0. And they're monotone because they're decreasing at each point the value is decreasing. So if I have a monotone bounded sequence, it converges. And at that point, we have that both of the virtual values are 0 and unironed. What I really needed was these overlapping iron intervals where there was no point be that many many options. And so it turns out that the menu complexity is always finite. So it's unbounded, it can be as large as I want, but it's finite. Okay? And so this is really a new realm for menu complexity. We had uncountably infinite, we had polynomial and exponential, and now we have it's unbounded but finite. Okay. Questions about that? Yeah.
Do you have any understanding about what properties of a distribution might cause menu complexity to be substantially reduced? So, you know, I'm thinking of regularity and things in the single parameter regime,
Yeah.
but like, I don't know what the would be.
It's a great question. So there is a corresponding regularity condition in this setting which makes everything deterministic.
Yeah.
As far as anything in between those that just makes menu complexity reduced but not deterministic, that's a great question. The condition that is regularity here, so what is regularity? Regularity means that if you draw your revenue curves in quantile space, they'll be concave. But here we've been drawing revenue curves in value space so that we can line up with the other deadlines and match in value space since the IC constraint is in value space. And so the corresponding thing is that these revenue curves need to be concave, but one, they're in value space, two, they've been multiplied by the probability that because they're in value space, they've been multiplied by this probability that you'll buy. And so the correct condition is marginal revenues, or DMR, and it's exactly that these revenue curves we've been talking about is, it's exactly that they're concave, which instead of phi being increasing in quantile space corresponds to f times phi being increasing in value space. Yeah. Great question. Okay. So I want to introduce one more setting that also is in this realm, and this is the multi-unit grid. So this setting was introduced in a paper by Goldner, Ithaca, and Alex Somas at last year's EC. And basically, you have a bunch of different items that you want, and a buyer has some value for each item and a demand cap of how many units they want. So maybe they're creating documents in a word processor and they say, I'm happy for each document I can create up to 3, but I don't need more than 3. I know that I don't need more than 3. And so you can sell them how many options. Think of this as like different levels of plans for how many documents you can create in a month or something. And so you can sell them, do I want to sell them only 1 or 2 and 3, and again, you can segment your market. The difference here is that if I only get 2 documents and I want up to 3, I still get 2 V value for them. I just don't get 3 V value. If I get 4, I get 3 V value for them. So it's a slightly different correspondence to how I feel about the other options. And in the paper with Nikhil and Ariel and Raghavansh and Matt, the lower bound that we just constructed that says you need this unbounded menu complexity also applies to the setting. And the reason for this is because what does our ordering look like? It says, well, if I want 1 document, I'm happy with 2 documents. If I want 2 documents, I'm happy with 3. If I want 3 and I get 2, then I'm getting 2/3 of the value. So I am happy to some extent, and 2/3 is happy. And if I want 2 and I get 1, I'm happy at 1/2 extent. So there is this correspondence between how I feel about each one. And embedded in this graph is impartial ordering that says I'm happy with 3 if I want to, and I'm happy with 1 to 1/2 extent. And so because there's a partial ordering embedded, we can set up a similar one where we have to deal with this times 1/2 factor, and I'm not going to go into the details at all, but it's very similar. You can come up with a bad example where, again, complementary slackness dictates that you need so many options. Okay, so the point is multi-unit pricing is also unbounded. It's at least as far as partially ordered. Okay.
Do you know what to be doing?
No. Good question. Okay, so I'm just going to summarize what I talked about. I don't have anything anymore. I just want to make sure that we've got what we've talked about, which is we're talking about these settings which are multidimensional. There are different outcomes, but they're very highly structured. And what exactly is the common theme between all of these is that you, the buyer, have some most preferred outcome. I know how you feel about getting 2 or 4 documents. If you want Wi-Fi and phone, I know how you feel about Wi-Fi and TV or just Wi-Fi. Okay? So that's really the common theme between these 4 or 5 different settings. That's the common theme, is that there's this most preferred outcome, and telling me these 2 pieces of information tells me how you feel about all of them. Even though you may have very different values, because we're in this setting where it's structured. Okay? And so what comes up because of this are a bunch of properties. The first is that we can sort of collapse the allocation rule. I don't really need to reason about the fact that you're getting 1-day shipping or 2-day shipping or 3-day shipping. I just need to reason about the probability or to what degree you're happy. How happy are you? I know that you're half as happy if you only get 1 document when you want 2. So I can model it that way. I know that you're just the same happiness if you get more documents than you want. Okay? So instead of talking about the probability that you get all these different outcomes, I can just talk about how much value you're getting corresponding to your favorite outcome. Okay? This also means that I have these reduced IC constraints. I'm only worrying about do you prefer the next immediately preferable thing, which really helps reduce the dual and let us talk about what's going on in duality. Because even though we started with a primal that, I don't know if you noticed, was continuous and had infinitely many constraints, because these things reduce, we can actually talk about them. And finally, most importantly, we get these single-dimensional perks. We're in a multi-dimensional setting where there's so much structure that we wind up with these single-dimensional perks, such as the payment identity, and being able to talk about things in a much simpler way. Okay? So that's the common theme between these settings that we've been talking about. And so this is why we can map menu complexity to this much finer realm. And so the methods we've been talking about were revenue curves, where we talked about exactly where the menu complexity is growing because the prices are splitting into randomizing over prices. And there was this limit to splitting because we were dealing with just these straight lines in this concave upper bound. And then we talked about how you can also even do approximate revenue and limiting your menu complexity by polygon approximation because we're talking about revenue curves. And now we've been talking about complementary slackness coming from duality, which says, where are certain outcomes preferred? Where do the complementary slackness constraints tell us that you better prefer this outcome to this outcome? And where must the allocation be positive? Where does the allocation need to be distinct, which means that we're going to wind up with multiple menu options and grow our complexity? And what are the limits to this? How do we get upper bounds? We know that it can't be more than this much. Okay? So this is what we've been talking about. And again, I'm just going to show you my pictures of how this plays into what's already known and what Yannai was talking about in the first half, which is we had this, for optimal mechanisms, we really knew very little about menu complexity. We had 1, and we had uncountably infinite, and then we filled out this gap with exponential and unbounded for the settings we talked about. Okay, we know very little for approximation, but we do know that for epsilon in the order of 1 over n squared, we have some approximation for FedEx, and this is a stronger lower bound because the setting is simpler.
So,
Yeah.
what is the, I mean, the bio myself and the sound paper from 2017, if you consider epsilon equal 1 over x squared to be fixed epsilon, then there we have epsilon equals 1 over n.
Okay, good. So I'm missing a point on the spectrum. Okay. And finally, throwing this back in, and again, like I talked about resilient results that I'm obscuring because I'm just trying to paint out this spectrum, where the bottom half is really just dealing with n independent additive items. And we add all these points for approximation and optimal mechanisms that fill out our spectrum. Okay. So now we have much we've zoomed in, as Yannai said we were going to, and filled out the spectrum. And I'm just going to leave you with some of the problems. So some problems, what about more complex settings? So I've only talked about 4 or 5 settings. What if we have more complex where I know that if C is your preferred outcome, you feel some function of your value about A, or function of your value about B, and it's more general than just the multi-unit pricing setting where there's this nice fraction, or just happy, as it wasn't correctly ordered. What about lower bounds to get a 1 minus epsilon approximation in terms of any epsilon, as you and I talked about in this paper, as opposed to just for epsilon the order of 1 over n squared? That's the only approximation result we have is that one. What about constant factor approximations as opposed to 1 minus epsilon approximations? Or again, as Yannai said, this is a very interesting interesting open question to me is multiple bidders. What happens with multiple bidders? And also just filling out all of the questions that have been asked in more complex settings in these new highly structured settings.
How is the question defined for multiple bidders?
How is it, yeah, so this is the point that Yannai brought up in the first half, is that it's a good question to talk about what is the right notion of menu complexity for multiple bidders. And he suggested some options, such as the largest size of any menu, because your menu is determined by other people's bids. The largest size of any menu, the sum of the menus, what is